Hi, everyone. Welcome to the workshop on explainable and interpretable artificial intelligence for biometrics. So we are about to begin. We will just give some minutes for the ones that still didn't join us. In the meantime, I just wanted to remind you that the workshop is being recorded, and everyone is agreeing on being recorded when you are joining the conference. So if you don't want to be recorded, you can always turn off your video and you can pose your questions using the Zoom chat or the underlying platform that also allows you to pose questions by writing. So we will make sure that those questions are posed to the speakers in the end of each talk. So we will start in a few moments just with the opening session, and that will be followed by a keynote talk. Then we have an oral session, then another keynote talk, and a final oral session. In the closing session, we will just say goodbye and announce the best paper award of our workshop. If you have any question at all, just do not hesitate to pose to any of us, or even to use the underlying platform or the Zoom chat at any moment. We will be paying attention to the chat to try to help you as much as we can.
Not we can start the session.
Excuse me? So I think we can begin. We have a very tight schedule, so we do not want to waste any time, any moment. So this workshop is an event organized by Inequality, our research lab in Portugal, with the partnership of European Association of Biometrics. I will now give the floor to Professor Jaime Cardoso, which is one of our main organizers.
Thank you, Filipa. I will be very quick. I just want to welcome you all in the name of the organizing institution, Inequality. Inequality is in fact one of the largest research institutes in Portugal. We are roughly, I would say, 1,000 collaborators, and we are located in this beautiful city of Porto. Today is a bit cold, but we are really very beautiful, and if you have the chance, you should visit us one day. Inequality acts as an interface between the academia, the university, and the industry, trying to bridge both parts and helping on the transfer of knowledge between them. And Inequality is indeed very large. It's a research institute in the engineering field. And within all our centers, our groups, there is a very strong group, I would say, in computer vision and machine learning. And within this group, there is a team that selected biometrics and forensics as a target domain, as the challenge. And it was this team that identified the relevance of this topic, of this interpretability in AI for biometrics. And it was this team that put forward this workshop with the help of other colleagues in computer vision and machine learning group, Filipa, João, Wilson, Tiago, Sarah, and so on. They are the ones that are behind all this. And we really think it's a timely event, hopefully maybe the first of a series. And I just have to acknowledge everyone, all the organization from general shares to the program committee, publicity and sponsorships and so on. All our reviewers, our technical committee, sponsors, and the invited speakers, and the authors for sharing their work with us. And well, all you, the participants that make this possible. And in the end, I hope that we can together have this, let's say, high-wielding event that in the end, everyone benefits. So I hope that you enjoy, and please do more than just assisting, participate in the event. Okay? Thank you.
So, like Jaime said, we are welcoming two keynote speakers. First, we will welcome Professor Peter Eisert, that will give us a talk on explaining deep neural network decisions for enhanced biometric systems. Hi, Professor Peter Eisert. It's very nice to meet you again.
Yeah, hi, Anna.
Hi.
Also nice to meet you again.
We will hear you shortly after the opening session. And after the first oral session, we will have Professor Cynthia Ruthing, which will give us a talk on the topic at the two extremes of interpretability in machine learning, very sparse models and interpretable deep neural networks. We have the schedule here, and it's also available on the underlying platform or our website. And as you can see, we have 2 oral sessions that are composed by 5 papers that were accepted in the workshop. And we will finish with a closing session with the best paper announcement and some final remarks. We would like to thank again to the members of our committees that made this workshop possible, and our supporters, so the European Association for Biometrics that were our partners, the Computers Journal, the Data Science Portugal, and the Data Science for Social Good Portugal. So if you have any question or any problem or any difficulty at any moment during the workshop, you can reach out to any of us that are here. We are identified by our names, so please do not hesitate to contact us. And now we can move to our first keynote talk. I will give the floor to Professor Peter Eisert. I will stop my screen sharing so that you can share your screen, okay? I will make you a co-host too.
Oh.
Perfect.
So now I have to ask you, do you see my slides?
Yes, we can see them.
Okay. Hopefully. Okay, then thanks, Anna, for the invitation. It's really a pleasure to be with you again. So unfortunately, it's not a physical, but a virtual meeting. So it would have been nice to meet also in reality, but maybe that's something we could make up at a later event. Yeah, I'm going to talk a bit about explainable AI for biometric systems, and in particular, making biometric recognition systems robust against attacks. And I will show you some ways how to use explainable AI in order to improve these systems and to make it more difficult for attackers to attack such systems. Yeah, I'm working at Fraunhofer HHI, heading a department there. Fraunhofer is similar to Inequality in Porto. It's a research organization. I'm also professor at Humboldt University and host a research group. And we are mainly working on image and video analysis in different kinds of application. And security is one of our application of interest that where we have several activities in analyzing images, videos, faces in order to make, for instance, such e-gates more secure. And in this talk, I will also focus on the problem of verifying a person's identity. And this is something that is relevant for for instance, for automated border control. So if you have been at an airport, which might not be the case in the last time, but everywhere there are popping up these automated border control system where you can identify yourself automatically. So you put on your passport and then the system uses a camera, capture your face and verifies if you're actually the person who you're supposed to be. And this way, the system makes sure that no one can enter a certain restricted area. And this is also something that is interesting for a broad range of different applications. So for instance, for every sovereign task you want to do online, maybe. So if you have a kiosk solution shown here in the middle, you might want to apply for a visa, and also this system has to make sure that you are actually the one you're pretending to be. And this also applies not only to sovereign tasks, but also to commercial things. You have maybe access control to restricted areas. You want to unlock your mobile phone or your computers, you have to verify your identity. And also very recently, there is a lot of activity in verifying a person's identity with some kind of video chat. And for instance, if you want to open a bank account. And for all these problems, you have to verify that you are the right person in order to do to access an area or to do some administrative task. And for that, you can use biometric systems. There are broad ranges of different information that you can use. So in this talk, I will focus a bit more on the face, because that's a very convenient system in order to identify a person. It's contactless, so you don't have to touch anything, which is very advantage for also here in this pandemic time. You can capture from a distance, and it's also very widely accepted as a tool for verifying a person identity, which might not be the case for other biometric features. And face recognition is now a mature technique. It works very well in spite of different challenges like head pose, illumination, aging effects that you have, and that make face recognition a difficult task. So everything seems fine, but there have been many different kinds of attacks recently published or in the last time, and also the technology advances makes it possible to attack such kind of face verification system. They also apply to some extent to other biometric cues like the fingerprint, but here I focus on faces. So for instance, there are face morphing attack where you use multiple images, or in the easiest case, 2 images of 2 different people. You fuse the images, you blend them into intermediate images, and if you can get this image on your passport, then both individuals can actually enter a system which is controlled by face recognition. So that's one threat. being published a couple of years ago. Then there's presentation attack, so you don't alter the image on your security document, but you can just alter your own appearance or just hold up an image, a video, a tablet, or anything in front of a camera. And especially if you are in a self-service environment, then this is a threat to these face recognition systems. And very recently, we have seen a lot of deep fakes, which makes it now possible to synthesize new humans or to change the appearance of one human and replace that by another one. And this is, for instance, a threat for these video ident systems where you do a video chat with another person and you can pretend to be someone else, which you are not. And in the following, I will show you some work that we have done in order to detect such threats for these 3 examples. And then later on, I will show you how we can make these detectors more robust using different kinds of explainable AI. So first example is presentation attack. And as I mentioned, this can be easily done by just putting up an image into a camera. And if there's no one looking at you, then the camera has a difficult task in distinguishing a picture of a picture or the picture or the person itself. So since the camera is 2D, then the picture is also 2D. You can also place the image maybe on a t-shirt, which might not be that suspicious, rather than holding up an image. The image can also be animated. For instance, if you have a tablet and then just hold it in front of your face and then show an animation of someone else. You can use 3D techniques. 3D printing is available. You can print a face which you can capture from other pictures using photogrammetry. And yeah, here this is also one example where some guys have hacked the iPhone and opened it using also some kind of a mask. And yeah, this was then possible to fake the recognition system. Yeah, so you can either show something into the sensors or you can just modify your own appearance. Here are just some examples for mask. Here in the middle, you see one example. This is actually one known threat. So this young guy has modified his appearance and pretended to be this old guy, and then he went through a passport control and was later detected. But you can also, instead of wearing entire mask, also use partial mask, change noses, or just using accessories, makeup, or anything else in order to shift your appearance towards another person and to make it more difficult for the face recognition system to detect you. Yeah, so this is a threat to several face recognition systems, and we have been working since a couple of time on finding methods of detecting such attacks on face recognition system. And here we use a multitude of different small detectors which all look at particular details, and then by the fusion of all the individual detectors we can come to a decision whether the person is a correct face or maybe a presentation attack. And we look at cues, for instance, at 3D geometry in order to get rid of flat pictures or display. We look at liveliness detection using information about blood flow and pulse. We use eye blink in order to avoid static prints. And also we look at the dynamic analysis of curvature in the face in order to detect surface manipulation by mask, which have a different surface curvature dynamics. And I will just show you a few or 2 examples of classifiers that we use because I refer to them later in my talk. So the first detector that we have built tries to find out whether the person is a picture or a live person. And here we determine blood flow and pulse in the face, and this can be done by a regular RGB camera. And you have, due to the blood that goes through the face, very small variations in brightness and color in the face that you can use in order to determine pulse rate. This is a traditional thing, and you have certainly seen apps where you can measure your own pulse with your mobile camera. But now we extend that system and synchronize to the measured pulse, and then determine for each pixel local blood flow. So we have basically an amplitude of blood flow for each pixel, which is this SNR map. And in addition, we can measure timing to the pulse delay. So we have a pulse transition time map, which determines in which in which order or delay the blood actually enters the face. And from these two masks and information, we can now train classifiers to determine whether this is a live human or maybe a picture or a human wearing a mask. And yeah, this works rather well. So here you can see a human without a mask, so you have clear blood flow visible here. This person, or it's the same person, but wearing a partial mask at the nose, so you get some, which can be easily detected because of the missing blood flow or the lower available pulse. And the same thing can be applied here for this chin mask, which covers the chin. So here we have classifiers to determine whether you see skin or something else. And the question is, how good are they? How robust are they? And here we use explainable AI. I come to that later. Of course, maybe if you want to measure blood flow, you also have to measure other activities. So if someone wears a beard or glasses, you cover some areas. So we have another classifier that determines facial attributes, having, for instance, wearing glasses, beard, mustache. And this is like a typical deep learning problem, image classification. You put in an image and you get out a class. Here we have classes like gender, glasses, mustache, and beard. And you see they all work very well. High accuracy can be reached with deep learning. So these low values of 97% or 98% are just because for beards it's always difficult to tell whether one wears a beard because there are smooth transitions. Yeah, so we can use such classifier to determine which areas are interesting to analyze. And then we have other classifiers, for instance, looking at the geometry. Here we have different kinds of sensor, high quality sensors or low cost sensors like the RealSense. So we have basically a depth map. We can train deep neural networks working on depth information. And the goal is to distinguish a human face from a flat screen or from a picture of a human. And yeah, so we trained our neural network, and again, we got very good values. So we had 4 false positives for a rather small database, I have to assume, but this is due to the COVID situation. Currently, it's difficult to get test people, but this is these false positives are for each frame. So if you look at the longer frame rate, you can get a very high quality for that. But for all these classifiers, the question is, what have actually the classifiers learned? So the mask, the face attribute, the face geometry. So have we learned the right thing? And yeah, this is also true for another kind of attack. So I mentioned that face morphing attack is another type of attack that we are working on detecting. And the idea is for the attack, you take two images, you align them and create intermediate average views. And for instance, these two images are now averaged average views. So the face area here of these two people are identical. So this is pixel identical. And if you provide, so except for the hair, so we use the hair of just one original image, but the face area is the same here. And if you provide such an image to a face recognition system, those two individuals can actually be accepted by the face recognizer. So we want to find out if someone has modified the image. Therefore, we have also to create different kind of images. You can do that, for instance, by using two images, and it's a typical pipeline for creating face morphs, and there exist multiple tools that you can easily download. So we have implemented our own pipeline for doing that automatically. So you have two images. We search for certain face features that allows you to align the shape or the geometry such that the eyes are on top of the eyes, the mouth are is on top of the other mouth, such that they can fit together. And then we blend and between those images and create an intermediate view. And this works nice for the face image or face area. And as I've said before, the problem is basically the hair, because just blending different hairstyles is difficult. But since hairstyle is rarely exploited by these face recognizers, we just take the hairstyle of one of the original images and blend in the morphed face image. And then we have a morph, and we can use that as a training for our deep neural network that can detect now these morphs. Of course, you can create morphs also in a different way. Here, this is an example where we use a style GAN for synthesizing humans. So again, we have two original images. Oh, these are not original, but we optimize the latent vector of a GAN, of a style GAN, such that it reproduces a face image of one original. Then we create the latent vector of the other person, and then we can blend between those two vectors in order to get an intermediate person. And this is another kind of creation of morphs, which has some other properties. And yeah, here's another example for a female face morph. And yeah, the possibilities of GANs, they increase, so you can even create very high resolution, realistically looking images. So the background here is not correctly, but that would be something that you would have to correct in a post-processing step. These GANs do not only allow to move between two individuals, but you can also move in other dimensions, for instance, moving in the dimension of age, such that you can correct or move the age towards another one. So this is, again, the original image, and then we have created a younger version of this image and an older version of that image, and that's also possible with these scans. But here in the following, we use only the face morphs, the intermediate blending. And now the question is how to detect them. And we have a large European project called D4Fly, and there we work on different kind of detectors that try to find out whether an image is a genuine image, a real image of a person, or if it's a manipulated version. And for doing so, you can look at different kind of cues in an image. So there are methods, for instance, that look at the low-level details, for instance, at the camera sensor noise, at compression artifacts, and other statistical characteristics. You can go a bit higher up and investigate statistics about gradient and blurring and sharpness of the images in order to find out if everything and all locations in the image are in the same statistics. Or you can look at high level artifacts, and that's more what we have been doing in order to find out if the images have been well aligned. So here you see, for instance, some artifacts due to misalignment of the highlights. It can also be semantic properties by mismatching highlights in the eyes, left and right, asymmetries, double eyelashes here, or other kind of artifacts. Yeah, and if you want to detect such kind of artifacts, you can now use genuine images and these morphed images and train a binary classifier, and that's what we have been doing. So we use different kind of deep learning architecture, for instance, VGG19, and then fed that with original views and face morphs, and we could very reliably detect these errors, these face morphs. So we ended up with the equal error rate of 3%, which is a very high risk of an attacker if he get caught with 97%. So it's very difficult for the attacker to pass through that system. The question is, how good is that really? And the last example that I would like to give is deep fake attacks for video ident systems. So usually if you open a bank account, you can do a video chat. So you talk to someone in a call center. At some point, you show up your ID card, and then your identity is verified. But since everything is digital, you can just insert another video stream, put in another camera, capturing yourself, manipulating the video, and send a manipulated video. So for instance, you can manipulate the ID card, so you can track that. We have done that here for another object, and then replace some information on that or the passport image. But yeah, the most problematic attack would be that you can replace your own appearance. And we have now a new project, also a national project, Fake ID, where we work on detecting such kind of deep fakes, but for the particular use case of these video ident systems. And one attack would be to replace the appearance of one person by another one, which is called face retargeting. So you have one person sitting in front of the camera, which is the attacker. Then you have the target identity, and you can use the motion and the expression of the original guy and then apply it on the target identity, and then synthesize a new video with another person. And deep learning and autoencoders make that possible. And you can animate from different sources, from audio, from video, from feature points, from speech, text, and so on. So this is, their deep neural networks have achieved a very remarkable quality, and you have certainly seen deep fake videos of Obama and many others, Mark Zuckerberg, there was a nice video. And we are also working on creating such kind of deep fakes in order to train our detectors. So what we work on, we don't synthesize the entire frame, but we use some kind of model information. This is some very rough tracking of the face, and then we put on the video on top of that and only replace the video in the facial area. And for that, we also, as many others, we use a variational autoencoder. So we put in the video on the encoder side, create a very low dimensional representation of the appearance and expression of a human person. And then we can use the decoder to synthesize again the original video. And since we do that both for the texture and also for the geometry in order to have also shape for alignment with the true face. We can train that, and usually 1 minute of video is sufficient to create a nice animation. And yeah, from that we can then we add it again with discriminator in order to get higher resolution results. And now we have a small representation such that we can now animate arbitrary people. So here's just one example here. This is the original video, and this is an animation just from these small latent vectors showing the same video as here. And here we have another completely different animation where we just synthesize something from text. But we can now synthesize arbitrary individuals using text information, feature point information, or video information. And of course, now we have that data, we can train our network, and this is something we are still working on. But similar to the face morph, you can train neural networks and then determine whether this is a fake video or not. But similar to the other approaches, we are not sure what the classifier then actually learned, how he can detect which is a right person, a correct person, or a deep fake. And if the classifier also finds out that something is deep fake, we also want to show why the classifier thinks that this is a deep fake. And this is where explainable AI comes in. And yeah, the problem with all these deep neural networks are that they have an astonishing capability in different kind of applications, but they are usually black box systems. So they can do their task very well, but they don't provide you or don't give you insight why they come to a decision. And this might be critical, for instance, in safety or security, critical application like medicine, for instance, where you want to detect a tumor. You don't only want to know that there is a tumor, but also why. And the same holds for critical things like face recognition. It's not only that you want that there's a fake, but you also want maybe an explanation why there's a fake. And also another problem is that you, besides an explanation, you also want to know if the classifier has actually learned the right thing. And this might not be the case. And there is this clever Hans principle. So Hans was a horse more than 100 years ago that was supposed to be good in math. So you could provide mathematical problems to the horse, and the horse could answer them correctly. But of course, the horse couldn't. Oh, pardon, what's the question? Yeah, so of course the horse couldn't do math, but they found out that the horse learned actually to look at his trainer, and once the trainer saw the right solution, the horse knew that now there will be the right solution displayed. So the horse actually did all the math correctly, although it couldn't solve the problem. And this is somewhat the same problem in deep learning. So you can train a neural network such that it answers for your training set the right, or gives the right answers, but need not be general for new solutions. And this is especially important since neural networks might be very sensitive towards small variations in the input. You all know of these adversarial attacks. So for instance, if you have here an image and a classifier saying this is a stop sign, you can add a small, very small noise. It needs to be commuted in a certain way. You can put that on top, and although these images look almost the same, the classifier just tells something completely different. So network might do things that they shouldn't do, and so we have to make sure that yeah, we can get some insight or explanation why the network came to this decision. And there are different tools of doing that. So very old version or simple version is you just hide some parts in the image and look if the classifier still comes to the same idea. So if you want to classify this image and see if there's a castle in there, you can just mask some areas. And if you mask the castle, then maybe the classifier says, no, there is no castle anymore. And then you know that there might be a castle under this. And with that, you can also create some kind of heat maps, but it's very slow. And maybe not the best way of dealing with that. There are other tools that look at different gradient information and do a Taylor decomposition of the network. So for sensitivity analysis, you can look at which areas basically influence the decision of the classifier and what kind of pixels do I have to modify in order to get the most deviation in the classifier outcome. This also works, but since you have a lot of gradients and usually for very deep networks, this can lead to noisy versions. So there are other extensions by smoothing gradients or integrating over gradients in order to make that more robust. Yeah, I show here another solution, and this solution is yeah, one tool that had been developed by our colleagues at HHI. It's layer-wise relevance propagation, and there the idea is to do a forward pass and a backward pass in a neural network. In the forward pass, you put in your image, then you compute all the activations, you come to a certain classifier decision, and starting from this classifier decision, you propagate the relevance through this network layer by layer. So you start from the last neuron, and based on the weights that you have here, you determine which neuron of the previous layer were relevant for this decision. And then once you have that layer, you move to the next layer, and you can propagate that to the previous layer. And at the end, you have some kind of a heat map showing the relevance of the individual areas in the image. And this propagation can be done in different ways. So they provided different rules. For instance, you can do that according to the weights. This is similar to the sensitivity analysis. But this leads to some kind of noisy input. You can reduce noise and produce sparse results by adding a small epsilon in the normalization of the weights, meaning that if all weights have, or if all activations are low, then basically the relevance is put in direction to 0. So this leads to sparse solution. Or another rule could be to emphasize a bit more on the positive activations, positive weights. So here you have the regular weights, and then with the additional parameter gamma, you add only the positive weights, so shifting everything to positive activation. And you can see how the outcome of the heat map looks for this example and the class castle. Now you can combine, and this is some kind of recommendation they found out. So start for the lower layers with these weight-based or just LRP 0 rule, and then for the intermediate layer you try to sparsify the heat maps, and then having the gamma law here for the higher resolution. And if you do that, you get a heat map that clearly shows what kind of pixels actually led to a positive activation of the castle, here shown in red, or maybe in blue, which inhibits the the detector to tell that there is a castle. Yeah, and compared to sensitivity analysis, for this examples where you want to classify cars, you can get clear or at least better outline of these regions. And you can now use these examples in order to prove if a classifier works or has learned maybe wrong things. And here, these are examples for classifiers that were proposed in the Pascal-Vogt challenge, where they actually provided the right solution and classified the image correctly, but based on a wrong assumption. So here, this is an example for an image of the class horse, but when applying LRP, yeah, they found out that actually the classifier does not look at the horse for classifying horse images, but on the copyright tag. And this was due to the fact that in the training database, there were a lot of horse images having a copyright tag. So the classifier was clever and learned if there's a copyright tag, then it's a horse. But of course, this is not what you want. And the same here. Here, the classifier learned if there's water, then there's a ship, which might not be true. So this is something you can get with LRP or other kind of tools. Another nice example what you can do with these explainable tools is here an experiment that we did in the classification of here images showing magnetic surfaces, and there were some defects, some cracks in there that need to be detected, but the images were just labeled okay, or this image contains a crack. So there was not a segmentation or something like that. So it might be simple, but you see here, these are images without a crack. So there are also some other artifacts which need to be distinguished from crack. And although only the images were labeled, you can now run LRP, and LRP tells you which pixels actually contributed to the decision that this image contains a crack. And what you see is that you actually highlight the crack. So if you do some kind of thresholding, you can then basically segment the crack. And this is also one way of creating, for instance, labels for data sets where some kind of labels are missing. So here you just had labels for the entire image, but you can get pixel labels using LRP. Of course, this might not work perfectly, so you might have to correct these labels. Yeah, but now coming back to our original problem with all these classifiers for presentation attack, face morphing attack, and so on. And I showed you this very simple classifier classifying gender, glasses, mustache, and beard. So that worked very well. So we run LRP to verify that. And yeah, this works quite well. So we see here for glasses, LRP highlights the frame of the glass, which makes sense. So the classifier looks at the frame. For the beard, actually it looks at the region around the mouth. And for the mustache and for this entire beard, it looks also at these regions. So here in this case, we were very satisfied with the results. So the classifier that we learned or trained learned actually the same or the right thing based on these LRP results. The other example, presentation attack, where we looked at the depth map, which also very good results, but running LRP, we found out, oh, the classifier does not look at the geometry of the face, it basically looks at the outline, so at the depth discontinuity. So if there's a person, so we have something, the person and the background, and in between there's a jump, and the classifier only looks at the outline. And if you put on a tablet in front of your face, then the outline of the face changes, and this has been learned by the classifier. So that might not be what you want. So we found that out because now you could think of maybe printing a face image and then cut that out with the scissor, and then it would work again. So the classifier would fail. So we modified our classifier So we did some kind of face detection, and then we cut out the face region so we get independent of the silhouette. And here, yeah, for a correct face with a good sensor, then LRP tells us, yes, it's a face. Blue is against the face. Even for this low quality geometry of the initial real sense, we get a recent result. Most of the errors are actually saying, yes, it's a face. If someone puts some fingers in the face, you see the unoccluded areas are still saying, yes, it's a face, but the fingers are here marked in blue, so it's recognized. A bent image where you use a picture and then simulate some geometry, you see some regions might yeah, be close to a face, but others are not. And for a display, you get complete mismatch. And yeah, this is a nice example where explanation has actually led to a better classifier. And yeah, we can do similar things for face morphing detection. Yeah, as said, we had a very good result with our initial simple classifier, 3% equal error rate. But looking at LRP, we found out, oh, the classifier basically looks only into the eyes of the image. And this makes sense because the eyes have high frequency. So if there are artifacts, they're most easily be detected in the eyes. But if you know that, you could then create a face morph where you morph everything in the face except for the eyes, and the classifier would fail. So we found out, and then we did a similar strategy. So we created partial face morphs where we just replaced here the black area. So it was not black, but the black area was replaced by the face morph. So we just created a morph of the left eye, the right eye, the nose, and the mouth. And we trained a multi-class network that actually can determine which area is morphed and which is genuine. And thus we enforced the classifier to look at all different regions in the face. And then we removed the last layer of the network and retrained it for the binary classification, and that worked much more robust. And if you look now at the LRP results, so the classifier looks at different areas into the face. And yeah, and such a classifier is also more robust to other attacks. So this is shown here. So in the beginning, we had an equal error rate of around 3%. And for our multi-class enhanced version, we have basically the same equal error rate. But if we provide only partial morphs to the system, the naive approach basically breaks. And yeah, you could argue, yeah, of course, it has never seen such kind of partial morphs, so this is true. And the multi-class actually performs much better. But he has also seen these partial morphs. So this is not very astonishing. But if you now apply a completely different attack, which is here some adversarial attack, adding some kind of noise, which has nothing to do with these partial morphs, we found out, yeah, that the robustness is much higher. So if we apply this attack to the naively trained network, it basically breaks down. But this multi-class network, yeah, has a high recognition rate. And yeah, so we can enhance the amount of noise, and you see the more noise we add, the lower the accuracy get. But for a certain noise, and here in this area we have something, it starts being visible. We have a large gap between these naively trained systems and the enhanced trained that we experience through the explainable systems. And that motivated us of extending this approach, creating more variation of our input database. So we exploited also neural style transfer methods in order to enhance the morphs. And neural style transfer is a technique that you have certainly seen before. It's this nice method where you provide two images, one original image having the content, one other image presenting the style of an image, and you can then apply the style to the original image and then create a new image showing the content of the original image in the style of this style image. And of course, you can do similar things with faces. Get an original image of a face and some painting of a face, and then create something that looks like a painting of this original face. But that's not what we want to do, but we want to do the opposite thing. We want to create something from a face morph that has been computed from two original images, and this face morph might contain some artifacts. The original images do not contain artifacts, so we apply neural style transfer techniques onto the face morph in order to create an enhanced morph that has the content of the face morph, that looks like the face morph, but with the style of an original image. So here we have to provide two styles because we have two images in contrast to the original version. But then we say, oh, we want to have an artifact-free. The style is artifact-free, and we can remove some artifacts in the enhanced morph. And here you see magnifications. Here you see, some blurring and some kind of artifacts. And this gets much better if you apply this neural style transfer. And this also works for the entire face morph. So here it might not be visible if you look a bit in. I'm not sure if you see that through Zoom, but here you see all the skin pores and the eyes are much clearer and sharper compared to the original computed face morph by applying these style transfer techniques. Yeah, and then we tried to see or to measure the influence of such enhanced face morph attacks on different kind of face morphing detectors. So we investigated here 3 different detectors from the literature, some kind of edge feature based detector using SIFT and other features, a local binary pattern, statistical image features, and then our 2 DNN based classifiers, the naive one and the multi-class one, and we compared their influence on images that have been computed with the additional face morph enhancing techniques by the neural style transfer. So so we have different kinds of attacks. We have the simple morphs. These are just the usual face morphs. Then we have the enhanced, the improved morphs using neural style transfer, but we also tried other possibilities to enhance a morph by using some kind of histogram equalization or sharpening filters, which also enhance the quality of a blurred image. And now we measured the quality of these detectors. So this is measured at BPCER and APCER. So, and this one is the attack presentation classification error rate, and the other one is the bona fide classification error rate. And here the numbers basically gives you the percentage of morphs that are not detected by the classifier. And if we train the classifiers with simple morphs and then test them also on similar morphs, then we get some certain values, and all these detectors work quite well. If we just use enhanced morphs and the detectors have never seen these enhanced morphs, then basically all detectors break down. So they have a significant drop in recognition quality. And this is also the case if we use other enhancement techniques. So also sharpening or histogram equalization for all these. So one detector performs better than the others, but in principle, all of them degrade. And even if you combine techniques, so enhanced morphs plus histogram equalization, you basically add the error. So it gets worse and worse. So then we used also this enhanced morph, similar to our previous cases, for training. And yeah, so we had a new training database that had 50% of these traditional morphs and 50% of enhanced morphs. And if we then show the simple morphs, basically we get the same results. Nothing has changed. But if we show these enhanced morphs, now the detectors perform much better than previously. And of course, this is not astonishing because they have also been used for training. But yeah, these detectors also perform much better for the other techniques. So by just spreading the range of possible attacks in the training database, you get also more robust to other attacks, to unseen attacks that have not been seen before. And that's a nice thing because this makes it easier. You have to add variation in your training database and you get more and more reliably or more robust towards new attacks that might occur. Yeah, and a last thing that I would like to mention here is the use of these explainability techniques like LRP to support humans in order to show the outcome of a network decision to a user. And we have seen that you can use, for instance, LRP or another tool in order to find out if the classifier has learned the right thing. You can optimize your classifier and creating it more robust. But yeah, it might be something for a technical expert in order to evaluate these heat maps and these results. But it would also be nice if you can provide such kind of images to a non-technical expert, for instance, a border guard or enrollment officer. And for instance, if maybe some face verification is not correct, such that the recognizer say, oh, look at the nose. I think this nose does not match. Or if you have face morphing detection, that the system does not only tell you, oh, there is a face morph, but look at the right eye. This might be suspicious, and please have a closer look. And you can use these techniques for that, but there might also be some problems because these deep neural networks are very complex functions, and you have a classifier that has a very sophisticated structure, which makes it sometimes difficult to interpret the results. And this is shown here. Here we have again our partial face morphs, and we have just morphed the left eye of this guy. And everything else was genuine. And running our simple naive classifier, and these are average results, shows that that the detector clearly detects also this modification. But running our multi-class detector, which was trained a bit more sophisticated, ended up that for some people, actually the wrong eye was highlighted. So although we modified the left eye, LRP showed, oh, there's some activity in the right eye. And this is due to the fact that LRP shows what kind of region has a lot of activity or activation that led to a certain decision. And we found out that this classifier has actually learned to compare left and right eye. And due to this clipping of positive activation and negative activation, it can end up that actually the good eye is highlighted, although it's compared with the wrong one, but it's just incorrect highlighting. And this might be difficult for someone to interpret if his or her is not a technical expert. So we came up with a modification of LRP, which we called focused layer-wise relevance propagation. And it's very similar to LRP. So we have a forward pass through the network once we have applied an image. And LRP then starts from the last neuron and propagates the information back. And for FLRP, we just look at the first layers, the convolutional layers, which don't have the fully connected classifier information. We just propagate that information back to the frontmost part. And because these feature maps here are still localized, we get a very nice localization of the activation in the original image. Of course, we somehow need to find a certain activation from this layer because we don't use the back propagation from the last fully connected layers. And we do that by looking into the deep feature maps for those neurons which has the most variation between morphs and genuine images, and these images are initialized and then back propagated to the original version. And if we compare that with LRP, we get very similar results. So this is a phase morph, and both LRP and FLRP show similar results. They highlight the areas where the classifier thinks there might be some artifacts. But especially in the cases where the classifier is a bit unsure, or even if the classifier is incorrect, this FLRP can highlight still the suspicious region, even if they are not enough for the classifier to decide that this is a phase morph. So this is again a phase morph. The classifier had said, no, it's not a morph, but I'm not really sure. And if you look at LRP, because there was the incorrect decision, this does not show really the artifacts in the image, but with FLRP, we can now clearly see the artifacts still in the image, because this image here shows some clear blurring effects, while this eye here has a better blending quality. And also here there are some artifacts visually visible, and they are detected by FLRP. And also our original problem with the flipped eyes is circumvented by FLRP, because we are just looking at the convolutional layers. And here in this case, it's not a partial morph, but here this eye here is very badly aligned. So this has clear artifacts, which is highlighted here, and LRP has flipped here these eyes and show something in the other eye. And if you're more interested in this particular tool for visualizing classifier decision, there will be a presentation later this day in this workshop. So you're happy to be to join the talk there. Yeah, and with that, I would like also now to conclude my talk. I've shown you different kind of attacks on biometric systems, and also shown you that deep neural networks can really help in detecting these classifiers. And the main problems to make them robust against future attacks. And so we have also seen that broadening our database and putting in some variation in there is a very good strategy in order to be robust against unseen attacks. And in order to increase robustness, you can use explainable AI like LRP in order to find out if your classifier has learned the right thing. But you can also use LRP or FLRP in order to highlight to someone where actually a problem lies, and this can help in order to make a biometric system more robust if you have an automatic system, but also some humans that can check, which is, for instance, possible at an airport control. And yeah, all these tools are just very simple tools for classifiers, so it would be nice to extend them for other kinds of input, for instance, like video, and I'm very looking forward for new solutions there for enhancing explainability in AI. With that, I would like to conclude my talk. Thank you very much for your attention. And I also want to thank here my people in my group that have contributed to all these works that I've shown here. Thanks a lot. And yeah, if there are questions, I'm happy to answer them.
So I would like to ask anyone, if anyone wants to pose a direct question to the speaker, Professor Reisert. We don't have much time for questions, but if someone wants to come forward with a question, please do.
Yes, it's Alfonso Ortega. I would like to ask something, if I can.
Sure, sure.
I saw with interest your explanation about the use of variational autoencoder, and I would like to ask if it is possible to assign some semantic meaning to the features that these variational autoencoders can get from the images.
Yes, it's possible. So we actually tried especially that. So we put in a model in between, a blend shape model, in order to force the network to learn some semantically interpretable representation of this latent space. Right now, we have moved a bit away from this approach. We just use a variational encoder and use this exploitation of this variational part in order to get a very good maybe ordering of all the features, such that close by features have also close facial expressions. So this has no meaning at all. But then we put a mapping network in front of that in order to map semantically interpretable information, like, for instance, some feature points in the eyes to the latent vector. So the latent vector is just a representation that can be used in order to synthesize plausible faces with plausible facial expressions. And then we have an additional neural network that does the mapping, for instance, from feature points to these latent vectors, or from text to these vectors, or from speech to these vectors. And then in the beginning, we have these semantic values. We morph them to something that you cannot interpret, and then we have something again.
Mm-hmm. Thanks so much. Thanks so much.
Are there any other questions? If not, I would like to pose one question. When we are talking about presentation attacks, the question here is, we saw many examples of models providing correct decisions, yes. But when we see what are they basing their decisions on, it doesn't make much sense for the human expert. So my question is a bit, how can we evaluate in these scenarios if the explanations provided make sense to a human expert? And if you did any evaluation of that kind, and how can that be achieved, considering that the presentation attacks are so different and they will be spread among the face? How can we say if we have a good explanation for a decision or a bad explanation for a decision?
Yeah, I think in general, it's a difficult question because you have a very broad spectrum in creating some kind of an explanation. And even if you stick to a certain tool like LRP, you have a lot of parameters that you could address, and you get different kind of explanation for the same network and for the same result. But in principle, they have at least same tendency for the results. And for instance, for the presentation attack, I showed you that, for instance, the first classifier just classified the outline, and this was clearly could be clearly visualized with the LRP result. And the same holds for this enhanced detector, which could now distinguish areas which are in favor or against a certain decision. And I think these examples that I showed, which are of course not representative, but they showed in a clear way that it actually makes sense, and you could use that kind of information also to visualize clearly, look at that region. So in this area, I think there is a problem. And then maybe a human, it can be a human expert when optimizing the classifier, but also maybe in a live scenario, if you have someone, you could send the image to someone and he looks at the image and says, oh yeah, you're right, this is something suspicious. And yeah, then you can use LRP or other classifier results in order to visualize that also to a non-expert human.
Thank you so much. So we are already a bit 5 minutes late, but if there is any question still that someone wants to pose for a last minute, if not, I would really like to thank Professor Reiser for this such interesting talk. I think there is a lot to think about, and I was so eager to listen to your talk that I didn't even properly presented you in the beginning. So for that, I want to apologize.
No problem.
I really wanted to rush into the talk. So I would like to really thank you. And everyone here probably knows Professor Reiser. So I would like to thank you for the talk. And I know that you are going to stay with us. So if anyone wants to pose any question, I think you will still be available. So thank you so much. And I think
it was a pleasure for me.
Thank you. We will now continue.
Awesome. Okay,
thank you.
Thanks.
Okay, thank you very much. And now we will move on to the first oral sessions. As you know, we will play the author's sent video, and then we will have a short discussion where you can place questions to the authors, or during the presentation you can also include some questions on the Zoom chat or the underlying chat as well. And now the first paper is Explainable Fingerprint Roi Segmentation using Monte Carlo Dropout, which is presented by Indu Joshi.
Hello everyone, I'm Indu Joshi. I'm a PhD student at the Computer Science Department, IIT Delhi. Today, I'm presenting the research conducted by me and my team. The research is titled Explainable Fingerprint Roi Segmentation using Monte Carlo Dropout. Fingerprint matching systems are one of the most robust biometrics-based authentication systems. These are used for various access control, civilian, and forensics application. Although fingerprint matching systems are generally quite robust, however, it is observed that fingerprint matching performance is adversely affected due to presence of background noise. Fingerprint ROI segmentation is typically the first step in fingerprint pre-processing pipeline. This step is targeted to separate the foreground fingerprint and background region. By limiting the foreground fingerprint region, ROI segmentation helps twofolds. Firstly, it reduces chances of spurious minutia detection. Secondly, it reduces computation time for performing fingerprint matching. Fingerprints can be acquired through different sensors employing disparate sensing technology and leading to varying sensor and background noise. Generalization to different backgrounds originating from disparate sensors is challenging for ROI segmentation algorithms. Approximating model uncertainty provides a means to quantify models' confidence in ROI prediction. High uncertainty indicates the possibility of erroneous predictions. In this research, we use Monte Carlo dropout to calculate model uncertainty. In this figure, the first row represents the input fingerprint image, whereas the second row represents the model uncertainty predicted by the proposed work. In the uncertainty maps, blue color denotes low uncertainty values, whereas red color denotes high uncertainty values. As shown in the first and third column, around the noisy background regions, the predicted model uncertainty is fairly high. Similarly, in the second column, in the fingerprint region with low ridge clarity, the predicted model uncertainty is high. Now we summarize the research contribution. So, most of the models proposed in the fingerprint ROI segmentation literature are not end-to-end and require post-processing. As the per pixel label might change due to post-processing, therefore, true uncertainty cannot be evaluated on them using Monte Carlo dropout. Towards this, we benchmark the performance of 4 state-of-the-art semantic segmentation models on fingerprint ROI segmentation. Having found the best performing segmentation model among the evaluated models, we modify the network architecture such that model uncertainty in segmentation is obtained. To the best of our knowledge, this is the first work to introduce model uncertainty guided explainability in the fingerprints domain. We benchmark the performance of conditional generative adversarial network, UNet, CCNet, and recurrent UNet on fingerprint ROI segmentation. Now we present the benchmarking results. To evaluate the 4 models, we use 2 different evaluation metrics, namely dice score and checkered similarity. We find that our unit outperforms all the other 3 models on both the evaluation metrics. So our unit turns out to be the most effective baseline model for fingerprint ROI segmentation. However, as our unit is not an explainable model by design, we employ model uncertainty in network architecture of our unit to understand its confidence in prediction. Now let's talk about how to calculate model uncertainty. For a given test input X test, to calculate the output, the Bayesian neural network requires posterior of weights given the training data. However, the posterior probability of weights is intractable for a deep neural network. Variational inference is one of the techniques to approximate the posterior. It requires defining and approximating variational distribution and it is required to be close to the true posterior. Given a deterministic neural network, Gall and her colleagues show that by reparameterization of the approximate variational distribution as Bernoulli, it is possible to approximate variational inference from a deterministic neural network. Through dropout, one samples binary variable for each input and for each network unit in each layer. Let yi denotes the output of layer I. Through application of dropout, yi is equal to ri into yi, where ri denotes the probability of binary variable to take value 1 in layer I. Thus, ri is Bernoulli distributed. This demonstrates that Bayesian inference can be approximated from any deterministic neural network by incorporating dropout in its layer. After the introduction of dropout, this integration can be approximated by Monte Carlo integration over stochastic outputs. And then the model uncertainty can be approximated as the variance of these stochastic outputs. To approximate Bayesian inference from RUnit, dropout is used on each convolution layer. For a test input X test, the variance of the predicted output is the model uncertainty. Next, we find that Monte Carlo dropout not just helps to quantify models' prediction, but it also works like an attention mechanism. Through these examples, we show that DRUnit performs a better job in segmentation compared to RUnit. In the first and third row, we find that whole of the fingerprint image is incorrectly detected as foreground by RUnit, whereas DRUnit correctly segments the foreground fingerprint. In the second row, we see that some of the background region is classified as foreground by RUnit. However, DRUnit does a better job than RUnit. We also calculate Jaccard similarity and die score for both these networks and find that DRU network indeed outperforms RUnit on both the evaluation metrics. Next, we show some of the successful cases and see that the DRUnit generalizes over different data sets and works for different background and sensor noise. However, we do find that if the intensity in the background is very similar to the intensity in the foreground, then DRUnit sometimes makes erroneous predictions. Next, we show the uncertainty predicted by DRUnit for the successful and failure cases. In the first two columns, we show failure cases of segmentation by DRUnit, and the other three columns represent successful cases. In the first column, complete fingerprint image is classified as foreground, whereas in the second column, the background towards the right is classified as the foreground. We see for both these cases that higher uncertainty is predicted, especially around the regions where indeed erroneous prediction has been made. We also see that the uncertainty predicted for successful samples is fairly low. We also evaluate DRUnit on three other metrics proposed in the literature. First one is erroneously classified patch percentage. This gives a percentage of erroneously classified 16x16 patches compared to the ground truth segmentation. We calculate hit coefficient, which indicates the relative foreground fingerprint area correctly detected by the segmentation algorithm compared to the ground truth. On the similar lines, we calculate mistake coefficient, which indicates the relative fingerprint area incorrectly detected as foreground by the segmentation algorithm compared to the ground truth. We find that DRUNet achieves competitive performance compared to the state of the art on all of the three metrics. We also compute Jacquard similarity and die score and find that the performance of DRUNet is competitive on some datasets while it outperforms state of the art on some other datasets. We argue that the better segmentation performance of state of the art algorithm compared to DRUNet is due to the availability of higher number of samples for training for the state of the art, as the state of the art model is trained on a 16x16 patch. Therefore, the number of patches for training is fairly high compared to DRUNet, as DRUNet is an end-to-end model which works on the whole image. State of the art requires pre-processing to predict the segmented ROI, where DRUNet is an end-to-end model, but it also outputs uncertainty map, which quantifies confidence in model's prediction. To conclude, experimental results and visualizations demonstrate the fact that introducing Monte Carlo dropout works like an attention mechanism and also provides models confidence in prediction. We show that proposed model correctly outputs model confidence by predicting higher uncertainty around highly noisy and incorrectly predicted fingerprint regions and low uncertainty values around regions with clear wrist structure and low background noise. In future, other methods on uncertainty quantification can be explored. We thank the HPC facility of Indria Sophia Antipolis for computational resources used in this research. I am partially supported by the Raman Sherpa Fellowship 2019. We also thank the French government and its National Research Agency for partly supporting our research. For any queries, you may write to me at the email address as shown on the screen. Thank you.
So thank you very much. I think Hindu is in the audience, in the virtual audience. Maybe we can see you as well. Okay. Hello. Thank you for your presentation. It was very interesting. And I ask the audience if there is any question. Anyone wants to start the discussion? You can turn on your cameras. Okay, maybe Professor Eisert.
Yeah, thanks for the presentation. That's nice work. Yeah, I have a question or maybe two questions. So one is, you mentioned that you not only get some kind of reliability values with your DRUNet, but also you improve accuracy. So the one question is, where does this accuracy increase come from? You mentioned some attention mechanism, but is it also maybe just due to the dropout that you add to the network compared to the other network? And the other question is, if you run your Monte Carlo sampling, can you say a few words how often you have to sample the network in order to get maybe some threshold or some probability for a correct result?
Yeah, thank you for your questions, and both are totally relevant. So to answer your first question, why do I believe that? Why do I say that it works as an attention mechanism? So firstly, of course, dropout works as a regularizer, but also the idea is that, so how, the question is that actually indeed minimizing uncertainty helps the model. And why so? Because let's say if I can give an analogy. So if let's say you are trying to ask a student, let's say some question, and he answers differently all the time, then it's a notion of that the model, that the student is not confident. So similarly, if the model is predicting high uncertainty, then it means the model is not confident in its prediction. So then when you are back propagating, so the loss is going to be high, because the variance term is also there. So the idea is that when it's trying to the model uncertainty will act as a regularizer, and it will in the process help the model to learn better features, so that the model is confident in its prediction. So that's the idea, that it's working as an attention mechanism. So it's helping to identify the regions where it is not confident, and at least come up with a value which is constant. So that's the first question. And this second question is about the Monte Carlo sampling. So so if I say that the limitation of this algorithm is that you have to sample multiple times, and then you have to, then the average is going to be the output. So of course the one of the parameter is the number of samples that you take. So in our understanding, as you increase the number of samples, the accuracy should improve. But since it was taking so much time to train, so we took 5 iterations. So and then also it took so much time. So, and given the data set is so small, so of course that is a parameter which can be worked out. So we took 5, but of course the idea is that if you increase the number of samples, then the model is going to be even better. That's the understanding.
Okay, thanks a lot for the clarification.
Thank you.
Thank you, Professor. And Indu, any other question from the audience? I think not. I have one last question, probably, which is focused on the insights that you can get for fingerprint recognition based on your work. You had some plots of Monte Carlo attention, and that could possibly be described as explanations of the decisions, right? And your task was for foreground and background segmentation, basically, as I understood it. But looking at the explanations that you got, have you found any part of the fingerprints that is less useful than the others? And could you possibly use those explanations to select the most useful parts of the fingerprint only? To, let's say, make the models more efficient?
So firstly, since my work is on segmentation, it's not in the matching. So the idea of what is important and what is not important, that comes that whether it's a foreground or it's background, right? So
Yes.
as I had also shown in some of the examples, that near the background and near the regions where ridges are not very clear, the model outputs high uncertainty, which it should, because if it is not confident, these are the regions where it should not be very confident. So we see that around the boundaries and around the areas where the ridge clarity is not very much, or maybe the intensity of the background and the foreground is similar, at that portions we see that the model uncertainty is high. So in that sense, yes, it does understand the ridge structure in the background. So we do get some insights, sure, for sure.
Yes. So thank you very much.
Thank you.
And we will move on to the second paper, which is focused on interpretable security analysis of cancelable biometrics using constrained optimized similarity-based attacks, and is presented by Henry Wang.
Good day. It is my pleasure having this opportunity to present our research. My name is Wang Hanrui from Monash University. This paper is authored by myself, Dong Xingbo, Jin Zhe, Andrew Benjin Tiao, and Machine Multi-Starity. This is an outline of my presentation. Let's start from the backgrounds. Cancelable biometrics is developed to raise security and protect the privacy of biometrics. There are 4 properties. Irreversibility means it should be computationally hard to retrieve original biometric features from a single or multiple compromised templates, even under the case where the transformation parameters such as token are known. Hence, the compromise of protected templates will not lead to the privacy invasion. Revocability means it should be feasible to reissue a new protected template when the old one is compromised. Other protected template should remain unchanged when the replacement is carried out. Unlinkability represents it is impossible to perform cross-matching among multiple protected templates across various applications. When one or multiple protected biometric templates have been stolen, the templates that derived from the same identity that is stored in other databases should not be traced. Performance preservation indicates the accuracy performance should not be degraded significantly after transformation. Here I list some notations will be used in this presentation. X and with head are biometric feature vector of original trait and pre-image respectively. R or B is user-specific token. It will be replaced when the user reissues the template. This is very important in our attack. H is protected template. With head means it is for pre-image, and with apostrophe indicates it's for reissuing scenario with different token. In our research, we conducted the experiments under two representative scalable biometric schemes called LM hashing and biohashing. The LM hashing is a ranking-based locality-sensitive hashing method. The LM hashing transforms a biometric template into a set of top-ranked discrete indices of random subspace projection as hash code. Biohashing is binary discretization process to transform biometric feature vector X to a set of binary code. However, existing research has claimed that cancelable biometrics is vulnerable to several attacks, such as ARM, also known correlation attack, or dictionary-based attack, and brute force attack. Our focus in this paper is similarity attack, also known as pre-image attack. Similarity attack exploits the similarity preserving property of cancelable biometrics to generate a pre-image from the protected template. The pre-image is an instance despite not close to the original biometric template. After the transformation, it is highly alike to the targeted protected template. The main contributions of this paper are: first, we propose a constrained optimization-based similarity attack called CSA. Second, we interpret pre-image generation problem from the supervised learning perspective, which justifies why CSA outperforms GASA significantly. GASA is the method we derived our CSA from, but without constrained optimization. Third, we conduct experiments to demonstrate the CSA against LM hashing and biohashing with LFW face dataset. We revealed the hardcode size is one of the key factors to impact the attack performance. Next, I'm going to introduce the method of CSA. CSA is still similarity attack, so it follows the basic concept of the attack. The ultimate aim of a similarity attack is to generate a pre-image X head, which is close to original biometric feature vector X. However, in cancelable biometric system, X is discarded after transformation. The transformed templates Y are stored in order to preserve accuracy. The relative distance between Y and the Y head are to be preserved. The problem can be reformulated to minimize distance of protected templates. So we define the loss function by the distance of protected templates. Here is a sample using notation of LM hashing. As I said, we interpret this problem as supervised learning because in similarity attack, the token used in searching pre-image is unchanged, but X is changing. We consider the token and the protected templates are paired X and Y as training data. just like a feature vector paired label. In terms of its transformation algorithm, we can consider X and Y have both L dimensions, so we can consider the size of training data is L. As we have known in supervised learning, to obtain a good verification performance, we expect a low loss value in training and low overfitting rate. We adopted the same way to improve the attack performance. First, I need to introduce some definitions. Test error is defined by the distance of protected templates of original biometrics and pre-image after we reissue the token. This is the main case we care about as we aim to develop an attack to generate a pre-image still works after reissuing the templates. Training error is defined by the distance of protected templates before we reissue the token. This is the loss value in training. Variance indicates the overfitting grade, so we use the differences of training and test error. N here is verification times as we run the test for 10 times to increase the generalization. As we mentioned the factors of good performance of supervised learning, in our attack, we minimize training error with constraints. We make it to 0 and alleviate overfitting with larger hashcode size. Recall the hashcode size is considered as the size of training data. This is the result to prove our theory. It is clear that with constraint training error, the blue line remains at the best level, it is 0. Although the variance, the yellow line is higher than XAI4, but with larger hashcode size, it reduces significantly. The test error of CSA is finally much lower than XAI4 under large hashcode size. In this slide, this is how we establish inequality constraint of LM hashing. Inspired by the ranking property, we identified the Z with index value equals H is the maximum value in the vector. So we built the inequalities by this reason. For different customer biometric schemes, such as bell hashing, we need to identify different constraints respectively. At last, we use ALGA to search the pre-image. The original GA is an unconstrained optimization problem, which is kind of ad hoc. ALGA is optimized for constrained searching tasks. It's an iterative 4-step procedure. Other than ALGA, there are more optimization methods where the constraints can be applied. In this work, we are more interested in the constraint optimization than the searching algorithm. So ALGA is only the choice of the implementation. Next, I will illustrate our attack performance. First, we select the partial data in LFW face dataset. We select the subjects with more than 10 images and choose the first 10 images of each subject. All the selected images are extracted to 512-dimension feature vectors by inside face. Our attack scenario is as displayed. First, we generate the pre-image with the first face image of each subject, assuming the users enroll the system with the first image. Second, after we obtain the pre-image, we reissue the template. Assuming the system is compromised and the user reissue the templates. Last, we generate the protected template with pre-image and the new token. Then access system, verify whether our pre-image is available to breach the system and the new token. This matching is conducted using left 9 face images of each subject. And here are our test results. Look at the bold number. Our proposed attack obtained over 99% successful attack rate with 512 hashcode size and 30% better than XAI4, which is without constraint optimization. This proves the effectiveness of our method and indicates that the better recognition rate leads to more security risks. For bell hashing, we get the same Conclusion, CSA performs much better than attack without constraints. However, the CSA model suffers from three limitations. First, the CSA relies on information leakage restrictively. This means it requires the knowledge of the protected template, transformation algorithm, and its associated parameters. Secondly, unlike GASA, which requires no constraints, CSA expects constraints to be established, which could be difficult for some cancelable biometric schemes, such as Bloom filter. Finally, the generated pre-image is not available to reconstruct the face images. In future developments of this research, the generalization of the CSA model against the other cancelable biometric schemes will be addressed. Moreover, countermeasures such as adopting nonlinear transformation or integrating permutations before applying the transformation to enhance the security of cancelable biometrics against the attacks, including similarity attacks, will be investigated. And if you are looking forward to a deeper discussion or any cooperation, you can contact us with email. At last, we appreciate a lot for the support of these departments and corporations. Here are some references in these slides. This is the end of my presentation. Now I leave the time to the questions. Thank you.
So thank you very much. Well, we already have the author here with us, and I have to apologize. Probably I mispronounced your name. I know because my name is João, so it's pretty common with me. So I apologize. And I ask the audience if there is any question to start the discussion. You can unmute yourselves and ask it. Otherwise, I have one question, which is related to your work. Basically, when you have your algorithm, which is based on cancelability, but there's another problem associated with cancelability or alongside cancelability, which is irreversibility. You need the templates to be irreversible. You don't want to recover images, face images from the stored templates on the database. Otherwise, if the database becomes compromised, you have a very big problem. And so the pre-images that CSA reconstructs are not realistic images, are not something that you can use to identify people or to inject in other biometric systems, or are they? Are they realistic? Can they be used to fool people as well as the algorithms themselves?
Until now, we didn't successfully reconstruct a realistic image. Actually, the pre-image, the instance we reconstruct is only one, you can say a feature vector of biometric template, which is effective to breach the final protected template. But actually, I tried to map to feature the vector. Actually, is different with original vector.
Okay. Yeah. Thank you. So it's still secure. It's not a liability. Okay. Thank you very much. Is there any question?
I would have one if I may. Thank you once again for your great presentation. It's like more of a follow-up question. It would be connected to the optimization algorithm that you use. So you use like a genetic algorithm, and my question would be, why did you choose a genetic algorithm to at least to optimize some of the parameters? What would be the other way around to do this? Because when you use some kind of heuristics, it's difficult to, I don't know, scientifically or objectively prove that they achieve optimizable parameters in every constraint. So I don't know if if you would think about this or not. It's more like a curiosity question on this type of optimization.
I'm sorry. Can you clear the point? Or what's your?
Yeah. So you use a genetic algorithm to obtain the pre-image, and my question would be, why did you opt to use a genetic algorithm to do that?
Oh, actually, that is not our. Actually, because in our work, we didn't focus on the searching method. This is not our focus. So we just choose one. Actually, this is just one selection. We choose, we find, and we choose, and it because the previous work used the GA, so we just use something related to GA, but have to works applies to our work because we use the optimization. But original the original generative the original GA cannot work in this case. So we choose another one for the constraint optimization. But this is not the, I believe this is not the most optimal searching method, but this is not our focus. We focus on the attack method.
All right, thank you.
Welcome.
Okay, so thank you. Any more questions? Okay, I think not. So thank you very much, and we will move. Okay, thank you. We will move to the third and last paper of this session, which is on symbolic AI for XAI, evaluating L-fit inductive programming for fair and explainable by an explainable automatic recruitment, and it's presented by Alfonso Ortega.
My name is Alfonso Ortega. This is our contribution to the workshop Symbolic Artificial Intelligence for Explainable Artificial Intelligence, evaluating LFIT inductive programming for fair and explainable automatic recruitment. We are Julián Fierrez, Aitami Morales, Zilong Wang from Lrp Research Group of the Universidad Autónoma in Madrid, Antoni Ribeiro from the Université de Nantes and the National Institute of Informatics of Japan. Our main goal is to check symbolic artificial intelligence to generate relevant, efficient, and human-understandable declarative explanations in classic statistical machine learning for biometrics domains. The current interest and need for explanations in these domains are our main motivation. For us, declarative explanations are declarative representations of functions and processes, in the sense in which declarative is understood in declarative programming paradigms. This is a fragment of the explanations we get for describing how CVs are scored by a neural network classifier. It is a set of ground first order logic clauses, propositional logic clauses in fact, that describes the conditions on the elements included in the CV for scoring it with a given value. There are several ways in which human beings formalize and handle their knowledge. They support different declarative programming paradigms. One of them is first-order logic, and Prolog is a popular logic programming. The knowledge represented by a Prolog program is easy to understand. This example shows the natural definition of the grandfather relationship. Your father's father is your grandfather, and your mother's father too. With an appropriate set of facts, you can check some well-known familiar relationship of the Spanish royal family. King Juan Carlos is Sophia's and Leonor's grandfather. We can briefly explain how symbolic artificial intelligence can face machine learning. Declarative programs can be automatically learned from examples. In the domain previously introduced, these are the grandfather examples. You usually have to include the background knowledge available to automatically write the grandfather program, a Prolog program in this case. Different kinds of automatic inference rules can be used by different inductive declarative programming engines to automatically write the declarative version of the knowledge implicit in the process. Given that human explanations are declarative programs are natural explanations for human beings. In this case, the grandfather program is itself an explanation of how to decide if King Juan Carlos is Leonor's grandfather or not. One of the most important characteristics of these symbolic automatic learners for our group is the theoretical support guaranteed by the inference mechanisms. This theoretical support usually implies that only relevant and efficient programs are learned. One of the main drawbacks in the current approaches to explainable artificial intelligence is to ensure that explanations are relevant and efficient. This means that no oversimplifications are made for efficiency reasons. Inductive logic programming is the term that usually stands for all these approaches. A rough comparison between numerical statistical machine learning and inductive logic programming highlights that inductive logic programming is supported by formal theoretical models instead of by the gradient of the loss function. It aims to discover how the choices are made instead of to which one is more probable. Due to its design, it is impossible to learn something different from abstract human readable declarative version of the processes, while it is usually tough for humans to understand the outputs of a neural classifier, for example. Finally, the statistical approach makes classic machine learning algorithms noise and error tolerant, although they require huge amounts of data, while inductive logic programming can learn from minimum data that have to be noise and error-free. Our general framework starts from a classifier seen as a black box by means of its inputs, CV features, and outputs scores. We have chosen as our inductive logic approach LFIT, learning from interpreting transitions, implemented as the Python PRIDE system. We fed PRIDE with all the available inputs-outputs pairs of the classifier to get a propositional logic theory equivalent to the system for those seen data. This is in fact a white box easy to understand by humans declarative version of the classifier that explains its behavior. In our experiments, PRIDE reads the whole datasets, both the inputs attributes included in the CVs and the output scores. It translates them into a set of ground terms, a propositional logic literal translation of the dataset. PRIDE iterates the reduction by domination inference rule to find the minimum set of rules with the minimum conditions to guarantee the logical equivalence to the classifier. This inference rule ensures that explanations are complete, explain all the cases, correct without spurious relationships, and minimal. Bodies contain the minimal conditions. The propositional theory is declarative, so it can be considered an explanation. It seems clear that these theoretical guarantees mean that these explanations are relevant. For getting our objective, we applied PRIDE to the 5CBDB dataset designed to study gender and ethnic biases in first CV automatic recruitment scenarios. This dataset is introduced in these references and described with more detail later. It has been slightly simplified for efficiency reasons. Face images are removed and non-discrete inputs are discretized. We try to get a positive answer to these two questions regarding the explanations that PRIDE generates. Do they give insight into the dataset's structure? Do they allow us to catch the biases when present? FiveCBDB contains 24,000 synthetic CVs, each including 12 features rated to the candidate merits and 2 demographic attributes, gender and ethnic group, along with a face photograph. 4 different scores are generated arranged into pairs, biased and unbiased couples, one for gender and one for the ethnic group. The input attributes of FiveCBDB are ethnicity, gender, education, experience, recommendation, availability, and from 1 to 8 different languages. They are named in this work as E, G, I1 to I12, and refer to the ethnic group, gender, education level, experience, existence of a recommendation letter, time needed to enroll the company, and proficiency level in 8 different languages. The output is the candidate score generated from human resources criteria. The last column shows the set from which they take value. Our goal is to compare biased and unbiased scores. So we run Pride on these scenarios. In order to study the gender biased, we get the logical version of the classifier from the dataset with input attributes G and I1 to I12, and we consider as output both unbiased and gender biased scores. In order to study ethnic bias, we get the logical version of the classifier from the dataset with input attributes E and I1 to I12, and we consider as output both unbiased and ethnic biased scores. The high level of abstraction of the propositional logic theory generated by Pride allows us to analyze the results from the occurrences of each attribute and value on the conditions of the clauses. To answer the first question, we will explain the structure of the datasets from these occurrences. To answer the second one, we define a couple of additional parameters: the global and partial weights of the values of the input attributes with respect to the different possible scores, the normalized percentage of frequency of each input attribute in a program, and the percentage of the absolute increment of each attribute comparing the unbiased score with the biased one. We normalize the percentage of occurrences frequency of an attribute, dividing it by the total amount of conditions to get a value from 0 to 1. The percentage of the absolute increment of an attribute aims to get as a percentage the absolute percentage of increment of an attribute from the unbiased to the biased score. For example, when scores are gender biased, the frequency of gender in the conditions could increase from 20 to 60. The percentage of absolute increment for gender in this case will show the value to 100% because 60 is 300% of 20, and so the percentage of absolute increment is 200. These are important details to understand the next graphs. This is the typical shape of all the graphs for the normalized percentage we have gotten. We can compare the unbiased and the gender biased case. We have checked with the authors of the datasets that the structure that this shape describes is correct. We can draw these conclusions. All the attributes are needed to get a score, although not all of them contribute the same. It is worth noting that those attributes used to bias are not the most relevant. Gender is highlighted in green in this case. There is another interesting characteristic in the structure of the gender biased datasets that will be commented later. The pure frequency of each value of each input attribute in the conditions of each value of the scores shows that after gender biasing, right graph, males get higher scores. You can see the difference is highlighted in green. The left graph, unbiased, shows an uniform frequency of scores by input values. You can also see that after biasing by ethnic group, right graph, ethnic group 1 gets higher values, while 2 and 3 get worse. The comparison of the normalized percentage of each attribute between the unbiased blue and gender biased red scores shows that gender is an attribute that increases the most both directly and indirectly. Here we have found another interesting characteristic of the gender biased dataset. We have checked with the authors of the datasets that they introduced random noise to relate gender and attributes I3 and I7, respectively recommendation letter and the proficiency in a specific language. This relationship can be explicitly seen in the graph. It is highlighted in green. Similar graphs are gotten for the ethnic group case. For the analysis of the percentage of absolute increment, we study the trend after different scenarios. This parameter summarizes the comparison between unbiased and biased scores. We start with gender and attributes I1 and I2, and add another input attribute 1 at each time. We get in this way 11 different scenarios for gender-biased scores. These graphs show together the percentage of absolute increment of all the input attributes in all the scenarios. We can see that gender is the greatest absolute percentage increment in all the scenarios. Remember that y-axis is a percentage of increment. For example, 200 for a given attribute means that its frequency after biasing is 300% of its frequency before biasing. The same can be observed when studying ethnicity-biased scores. The contributions of our work can be summarized as follows. Symbolic artificial intelligence is able to generate relevant, efficient, and human-understandable declarative explanations in biometrics. We have proposed a general methodology for generating explanations based on learning for interpreting transitions implemented as PRIDE. We discovered the structure of the datasets under consideration, and also the biases, both by gender and ethnic group, when present. In the future, we plan to explore how to increase the understandability of the explanations, because the propositional nature of the logical theory produced by PRIDE could become too much focused on the particular values hiding more general relationships. We plan also to explore PRIDE capabilities to predict scores for unseen data, not only to explain what happens on seen data. We plan also to provide the complete system with a by default automatic discretization step for non-discrete numerical inputs. We plan to start measuring the performance of the explanations to ease the comparison with other approaches. We plan to apply our methodology to other datasets in similar domains, and to compare our methodology with other similar approaches. Thank you for your attention. I'll be glad to answer your questions and doubts.
So, thank you very much, Alfonso, for a great presentation. And once again, I asked the audience to place any questions. Just unmute yourselves. Nothing yet. Okay. Yeah.
All right. Thank you, João. Thank you once again, Alfonso, for this interesting presentation. I try to study a lot of interpretable AI, so I really like this topic. My first question would be related to how would we approach this same framework within a computer vision problem, because I noticed that this inductive logic programming works really well in, let's say, tabular data or score-based data, but is it possible to apply this to an image, for instance, or to extract some kind of meaningful features from an image and apply this framework, which seems very transparent?
I hope so, because there are several inductive logic approaches. Logic is an abuse of language, because different approaches provide different declarative explanations, not only logic's one. But in this first attempt to check the viability of the methodology, we have started by the less expressive approach, that is mainly propositional logic, inductive propositional logic programming. But for example, I am aware, and I am following and trying to test also first-order logical approaches that have shown to be able to learn from a reduced set of images, much more reduced in amount of images, some relevant topics about something that could be interesting to learn. For example, the convexity or concavity of some images from the direction of the light or something like this. And so we think that it's possible to get similar results. But you are right. I agree that to handle images and huge numerical inputs are one of the most important challenges. This is why we are trying to add a by default discretization step in the pipeline. But we hope be able to get good results, taking into consideration also inputs as images and other real value inputs. I don't know if it was your question.
Yes, it's pretty much because from what I understand also from your work is that you somehow can induce some kind of, let's say, causality in your data. And for my interest would be if we could achieve this in images, because for instance, the first examples that you showed, so the definition of a grandfather, it shows really, so it's human understandable, I guess. So, and my question would be if we besides of extracting only correlations, if this framework could be used, let's say, to extract some kind of causality in tabular data as well.
Yeah, it's not the main point for us is to keep the model as close to the theoretical support as possible, because the theoretical support guarantees that what you get is relevant in a intuitive way. Relevant means equivalent, logically equivalent. So what you have seen from the scoring process is that it's going on expressed with the minimum conditions as a propositional logic theory. It's true that this is the less expressive approach. So, for example, for understanding properly the approach, I used deliberately first-order logic to introduce how symbolic logic, symbolic artificial intelligence faces machine learning, because it's much more human readable first-order logic. But it's more a comfort question than a logical question. Is both approaches give equivalent explanations. So the main focus for us is to keep the theoretical guarantees, because we are aware that to reduce or to simplify much more the system generates weak explanations that are useless. So we want to get declarative representations of the process. In this, one of the limits of this first approach is that it's more focused on the explanation itself than in prediction. But you can also get predictors from symbolic artificial intelligence approaches. So this is just a first step to check that we are mainly interested in symbolic artificial intelligence, not in a statistical focus one. So we think that the test is successful and motivates us to test other more expressive approaches to the same domains. So we think that is a good approach.
Thank you.
Okay, thank you. I think there was one other question from an attendee. Was it you, Professor Ivet?
I have at least one question.
Okay, yeah.
If I can post that. So you mentioned that for your logical analysis, errors in the data is a problem. So you need some consistent source data set. But on the other end, error-free data is always a problem. Is it possible to extend such an approach by adding maybe some additional constraints on maybe a maximum number of rules or whatever, and then finding a most probable solution that explain the data that you have, which then fulfill all the right thing, but which might not be consistent for all data entities? Is that possible?
Okay, if I have understood your question, there are two different two different points in your question. One of them is noise tolerance. You're right. This system comes from formal methods in theoretical computer science. So they are really they fail with noise and bad labeled data. But it is quite straightforward to extend the approach to handle noise and bad data. There are several attempts to do that we will follow if we need to face noisy data that more or less try to add an statistics phase for getting the most accurate answer possible. So it is not difficult to overcome this difficulty. By the other hand, you was mentioned something to guarantee some conditions on the, if I have understood, otherwise please correct me. Some guarantees about the program learned, the explanations learned, and this is done by default. The theoretical support of the models we use guarantee several properties. You could choose one of them, but most of them guarantee that you get the most accurate, the simplest version of the theory that explains your process. In fact, for non used to handle formal terms, you can see these guarantees as a measure of the complexity of the program you get. You can force to get or to learn the less complex version of declarative version of your process. The complexity depends on the paradigm you have used. For example, propositional logic is quite close to the exact values. First order logic shows more general relationship, but for example, functional programming is quite more tricky to understand because you have to be familiar with functional techniques, and there are also different approaches. All of them are equivalent in their expressive power, but differs on the comfort that the user feels when they read the explanation you got. So it's true, you can tune which kind of explanation you get, and by design, because it's a theoretical warranty, you can ensure that you get the most simple explanation that the paradigm can express. I don't know if it's your question.
Yeah, it was my question. Thanks a lot for the explanation.
You're welcome. You're welcome.
So thank you very much, Alfonso, and thank you to all the authors once again. And thus we conclude the first oral session. Thank you. Felipe, maybe you want to say something? No.
Yes, I think we can give just we are 2 minutes delayed, but I think we can still give like 2 minutes break because people have been here for 2 hours and a half almost, and we could start at 25 with Professor Cynthia Rudin's talk. So just 2 minutes break, and we will be back in 2 minutes. If it's okay with you, Professor Cynthia?
Yes, everybody definitely deserves a break after 2.5 hours.
Thank you so much. So 2 minutes and we will be back. Thank you.
In the meantime, I'll test if I can share my screen, make sure that works.
Sure. I think I need to give you permission, so I will do that.
Oh, I don't.
Okay.
Great.
Great.
Yeah. Okay, so I can stop. You can see it, right?
Yes. Yes. It's working perfectly.
Great.
Great.
How's the workshop been so far?
In my opinion, it has been going well. These things are always more, I think, more exhausting in this way. I think it's not the same as being in a room, but I think it has been very interesting. We started with a talk with Professor Peter Eisert, and then we had 3 papers already presented. So, and now we are going to your talk, so it will be great. And 2 more papers to finish.
That's
I
great.
think it's a good start for ACV, I hope.
Definitely.
So I think when Professor Jaime wants to start the introduction, you can.
Yes, I was just giving 1 more or 2 minutes.
For sure, for sure.
It's very tight, your break.
Yes. It means that the discussions were, people were making questions and discussing. It took longer than we thought.
Okay.
Okay, Philip, maybe just 1 more minute then, and then we start. Yeah. So I think that we can slowly start now this second part of our workshop, basically. So what are we missing now? We have now a second invited speaker, Professor Cynthia, and after that we have then the final round, final session with the accepted papers, and then we have the conclusion of the workshop. So please stay with us until the end. And now it's my pleasure now to share this session together with my colleague Sarah, and it's our pleasure to have Professor Houdin with us today. In fact, I have to say that it's second time that I try to have Professor Houdin in a workshop that we organize. Last year we organized a workshop in MICAI in interpretable machine learning for medicine, basically. Unfortunately, at that time, it was not possible to have Professor Cynthia, but now we didn't give up, and now we are fortunate to have Professor with us to share her work and experience and view of the field. Professor Cynthia works at Duke University and directs the Prediction Analysis Lab there, focusing on interpretable machine learning. And Professor Houdin received several awards, It's a 3-time winner of the Inform's Innovative Application in Analytics Award. And last year, or 2 years ago, in 2019, was elected as a fellow of the American Statistical Association and of the Institute of Mathematical Statistics for the work and for the contributions in this field in interpretable machine learning, and also in large-scale medical databases, and so forth. And therefore, it's really a central researcher in this field, and I think we are really quite fortunate to have Professor today with us, talking about, let's say, two aspects. I think one part will be about shallow methods, if I can say so, about scoring models, and the other about the deep models. And I think so it will be quite interesting to see how all this fits together, how interpretable models fit on these two endpoints of the spectrum. Professor Cynthia, thank you again, and the floor is yours.
Thanks. Okay, let me just share, see if that works. Okay, you should be able to see that. Great.
Yes. Yeah.
Okay, yeah, so I've been working in interpretable machine learning for, over a decade. And so today I'm going to talk about two extremes, very, very sparse models, linear models with integer coefficients, and then interpretable deep neural networks for computer vision. So the two extremes. I just need to start with some definitions. I'm sure you've heard these several times today, but essentially an interpretable machine learning model is constrained. It obeys a domain-specific set of constraints so that a user can better understand it. And I have a technical definition that lists a bunch of these types of constraints that you might want to put in, like monotonicity, causality, or generative constraints, or whatever. Okay, and of course, there's a spectrum between machine learning models that are very, very sparse, where you can really understand how the variables are jointly working together to create a prediction. And then on the other end of the spectrum, models that are just loosely constrained to be like monotonically increasing along one variable or something like that. And so why do you need interpretability? And of course, we need them for high stakes decisions or for when you want to troubleshoot. So I've listed a bunch of applications there: criminal justice models, credit scoring, air pollution, airplane maintenance, biometrics, anything that's really high stakes where you don't want to make a mistake. All right, now, evidence does not support the interpretability accuracy trade-off. I know a lot of people would really like it to, and a lot of people really say it does, but it really doesn't. And people will go to great lengths to demonstrate that such a trade-off exists when it isn't there. And so I'm going to just talk a little bit about this image for a while. So this is from the DARPA Explainable AI BAA. And here it's supposed to show an inverse relationship between learning performance, so something like accuracy, and the effectiveness of an explanation. Now, the first thing that I noticed when I looked at this figure, which I found very disturbing, was that it's not real. There's no quantification of the axes. There's no data set that this corresponds to. This is just somebody who created this in PowerPoint. This is like President Trump with the Sharpie. It's like somebody drew it. There's nothing in this image. And so I was like, okay, well, hold on a second. Let's pretend that this actually was quantified. So what is it trying to show? It seems to be indicating that somebody tried a bunch of machine learning methods on a single data set and then plopped a bunch of points there, showing that as the model gets more accurate, it's less effective in terms of explanations, and as it becomes more interpretable, then it's less accurate. And I was thinking, but this looks like they're working with a static single data set and a fixed evaluation metric, but that's not the way we do things in data science. In data science, there's a pipeline where in any data science process, like the KDD process or the CRISP-DM process, you're supposed to interpret the results after you get them. And then the information you get by understanding what happened feeds back into improving the data set and improving your performance metric. And so the fact that you could actually understand what's going on helps you improve the whole process. So this idea of a static data set and fixed evaluation metric is simply wrong. And then also the trade-off doesn't happen like this, even if you had a static data set and a fixed evaluation metric. In most cases, in in most tabular data sets, it's pretty flat. And if you're working with computer vision data sets, it's very different, but you can still get exactly the same learning performance with substantial explanation effectiveness, or whatever that means. So this trade-off really doesn't exist, even with a static data set and a fixed evaluation metric. And then also, this particular example didn't tell you whether they were talking about explaining black boxes or actually designing models that were inherently interpretable. Now, if you're explaining black box, fine, yeah, then it's approximation problem, and you're going to see a trade-off like this. But if you're actually trying to design a model that's inherently interpretable, there is no trade-off for every problem that I've ever seen. So, and it turns out that this particular image was supposed to represent explaining black boxes, and the author did not realize that there's a chasm between these two concepts. I'll talk more about that. Okay, so there's really two different kinds of problems. There's sort of tabular data where all the variables are like real valued or categorical or binary. And I always end up with tabular. I don't know why, but somehow the problems I end up working on are like, there's always tabular data involved. But there's also raw data on the other hand, which is like image processing data or sound waves or large amounts of text, where in these types of raw data problems, like an individual pixel is not a good predictor of the outcome. And you really wouldn't want to look at an individual pixel by itself. It's not really meaningful as a feature. And you wouldn't want to create like a sparse model in pixel space. It doesn't make any sense. So here the definition of interpretability has to be different than what you would typically use over here, which would be kind of decision trees, models like that. So now for raw data, the only technique that's really working right now on these kind of raw data problems are deep neural networks. But that doesn't mean that they can't be interpretable. So I'll go through later some examples of interpretable deep learning models that are just as accurate as black box ones. But again, the definition of interpretability is kind of funky. Now for tabular data, with minor preprocessing, so as long as you're willing to do that level of preprocessing, you can pretty much always get the methods to have very similar performance. And that includes very sparse models like sparse decision trees and sparse scoring systems. And it's surprisingly true. Like it's really hard to beat logistic regression models for a lot of tabular data problems. I even wrote a song recently called "I Can't Beat Logistic Regression." So it's kind of an interesting aspect of these tabular data sets. And this is why people for years were saying like, we're overfitting the UCI machine learning repository. Like we actually can't beat logistic regression. Now I say this, but then a lot of people say, but no, you're wrong. You must be losing accuracy because these models are constrained, right? When you add an additional constraint, it limits the flexibility of the model. And so it can't possibly be as accurate as the black box models. And you would think that black box models would be more accurate, but it's really not even usually the case. But it depends on your ability to choose a good definition of what interpretability means so that you can incorporate the constraints and effectively optimize that combination of the constraints and the accuracy or the performance metric. And in most cases, interpretability actually helps accuracy because you understand what you're doing and therefore can do a better job of it. So I'm going to give you an example where a lack of interpretability leads to errors in practice, and no amount of explaining your way out of a black box will actually help the problem. So this is an example of where a typographical error can lead to years of extra prison time. And in fact, it has for many people. And of course, this is the COMPASS example that I think you're probably all familiar with, where there's a black box model. It's used widely across the US criminal justice system, and it's used to deny people parole. Now here, this example is where someone was denied parole. This is a person who was in prison since he was a child. And then he was a model prisoner for some 17 years or something. He comes up for parole, it's denied. And he found out only afterward that it was because of a typo in his criminal history features, because he compared his score sheet with somebody else's score sheet. So he said, okay, I wonder if we actually need this black box model. And so at the time the Florida data set came out for COMPASS, we actually took the data and compared it with the latest machine learning method from our lab to see, do we actually need this black box? So we compared COMPASS with corals, which was our latest method that we derived in 2017. And in our 2017 paper, we took the Florida data, tried to predict outcomes, and we ended up with a model that fits in the bottom of a PowerPoint slide. So the model is really tiny, and it basically says if you're young and male, predict that you'll be arrested within 2 years of your COMPASS score calculation. Else, if you're a little bit older and you have a couple of prior offenses, predict arrest within 2 years of your COMPASS score calculation. Or if you have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and thought, there is no way this thing can be as accurate as this fancy black box that's used in the justice system that uses 137 factors, most of which we don't even have. But we were wrong. So this is tenfold cross-validation accuracy for COMPASS and corals. The different colors are different folds of the data set, and they're about equally accurate. And not only that, we tried a whole bunch of other machine learning methods, just the whole, just send all of them in there, and they all were about equally accurate. And some of these are really black boxes like COMPASS, which is proprietary, but also boosted decision trees and support vector machines with radial basis function kernels and so on. And so we thought, okay, there was this huge debate about algorithmic fairness of COMPASS, but the truth is that we just don't seem to need COMPASS at all. Like we can get away with very simple models. So it's not clear why we're even still using COMPASS. I mean, I'm not saying that we should use this model, right? Obviously this model has issues, but I'm saying if that model can do well, there's, we don't need COMPASS, okay? We don't need to have typographical errors in people's scores causing problems. And again, no way of explaining COMPASS is going to get you out of this mess. Now, for many problems that I've worked on, for all of the ones that required interpretability, we were able to create a model that was interpretable at the same level of accuracy as black box. And when I say accuracy, I mean just sort of general performance measures. And I've worked on a lot of different applications, and here are some of them, all of which required interpretability. Okay, so what I've shown an example of is, the fact that for tabular data, we can often have very sparse models at the same level of accuracy as a black box. And so what I want to do is kind of harp on that a little bit more and talk about kind of how you construct these very sparse models and show an application where we do it. And then I'll switch over to the raw data problem and go to the other extreme. All right, so scoring systems are sparse linear models with integer coefficients. These kinds of models are used very, very heavily in medicine. So here's an example of one scoring system. It's called the 2 helps 2B score. So why is it called that? Because it's 2 HELPS and then 2 points for the B. So the doctors can memorize the model just by knowing its name. And this particular model is designed for neurologists to use to predict seizures in patients who are in the intensive care units of hospitals who are at risk for brain seizures. So let me tell you a little bit more about that problem, and then I'll get back to the 2 helps 2B score. So let's say that you have an aneurysm in your brain and it bursts. So what that means is you have a hemorrhage and there's blood actually in your brain. So this is a brain hemorrhage and the person has blood in their brain. And for these patients, they would get surgery and be placed in intensive care and be monitored with continuous EEG monitors. So these are monitors all over the patient's head, and they're designed to detect seizures and predictors for seizures. And these are not seizures where the patient's shaking. This is a seizure only in the patient's brain. So the only way to detect it is with the EEG monitors. Now, seizures are very common in these kinds of patients who are critically ill, and seizures can lead to brain damage. And in fact, this is so dangerous. The seizures can be even more dangerous than the original hemorrhage. And doctors will go to great lengths to try to prevent seizures, to the point where they give the patient medication to actually stop the person's brain from functioning so that the patient won't have a seizure and the brain will be destroyed. So anyway, we need EEG to detect these kinds of seizures. However, typically in hospitals, there's not quite enough resources to go around. So there's a lot of the EEG monitors stay on patients for way too long, and then patients who need them don't get them. So we need a better way to allocate these monitors so that we can better treat these patients, better serve these patients. All right, so what doctors would do, okay, they would go, if you have a patient and they're ill, you would have all these scoring systems available. And in fact, there's tons and tons of these things. So this is a website called Medscape, and it lists literally hundreds of medical scoring systems. So if you went to the category for neurology, which is over here, you'd find a subcategory called seizure. And then you could look at the 2 helps to be score. And if you click it, it would show you, the questions that the doctor would answer. So there's the 2H, E, L, P, and then S, and then 2 points for the whatever. So anyway, that is this model right here. And then the doctor would fill in the points based on the brain activity of the patient, and then get a score. And then the score would translate into the risk for 6-hour risk for seizure. Now, this particular model is different than all of the other models in Medscape, in that it is actually a machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. It was built from over 70 variables, even though there are only 6 there. It's just as accurate as your favorite black box model on that same data set. It doesn't force you to trust it. Doctors can decide themselves whether to trust it. There's no additional explanation needed, because doctors can really understand how all the variables are jointly related to form the prediction. And they can calibrate the score with information not in the database, such as, I'm looking at this patient, they have this extra thing, I'm going to add another point for that thing, and then that gives me a better indication of the patient's risk. Okay, so the way that 2 helps to be was created is as a minimization of the following optimization problem. So there's 2 terms: the logistic loss, which keeps the model accurate and calibrated to the data. So this will allow you to get accurate risks, just like logistic regression. And then there's a model size term, which keeps the model sparse. So this value here is just the number of non-zero terms. This is a regularization parameter that trades off between accuracy and sparsity. And then there's an additional set of constraints, which says that all the coefficients have to be integers between -10 and 10. And it just so happens that the solution came out as 1s and 2s, but it could have come up with any numbers between -10 and 10. Now, this model is just this particular optimization problem. I would think that this is the problem that doctors would want to solve anyway when they're creating these scores, right? They want it accurate, they want it sparse, they want small integers. They would go to great lengths to get these integers, right? They would do all kinds of rounding and blah, blah, blah of logistic regression coefficients. But this is the problem I think they ideally want to solve. Now, this is a mixed integer nonlinear program where the feasible region is the integer lattice. So it's actually a really hard math problem. But I think this problem should be solved by computer scientists rather than solved by doctors, right? I don't think we should hand them our problem. I think we should solve this problem and help them. And so this is the optimization problem that we solve that created the 2 helps to be score. The algorithm that we designed for doing this is a mixture of a cutting plane method with branch and bound embedded in it. So it's actually a pretty sophisticated optimization problem that actually allows you to solve this in a reasonable amount of time for real data sets. Okay, so now when the patient comes into the hospital with their hemorrhage and they get their surgery and the doctor is monitoring they're looking at their EEG signal, and the doctor says, okay, I'm going to look at the signal and I calculate that this patient has 3 points. And so they're high risk, and I would place them then on continuous monitoring for over 72 hours and start them on preventative medication. Now, so far, the 2 helps to be score was validated on an independent multi-center cohort. I actually was not involved in the validation study. This was our neurology collaborators who did this study. And they have found that after it was implemented in several hospitals, that it resulted in a substantial reduction in the duration of EEG monitoring per patient, which allowed them to better allocate the monitors to people who might need them. And this allowed them to monitor a substantial number more patients. So over twice the number of patients they could monitor now than they could before. And this allowed them to help substantially reduce the amount of brain damage that were experienced as a result of seizures and to help them save lives. So that's an example of how interpretable models can work and can be implemented in high stakes settings, including in intensive care units. So I want to switch over then to the other extreme and talk about computer vision. Okay, so for computer vision, as I mentioned, the big challenge is really to figure out what the definition of interpretability actually is and how to actually get that embedded into our neural networks. So I'm going to present two ideas, and this is the first one. And so, so what does it mean? What does it actually mean to have an interpretable deep neural network for computer vision? Well, I want to start by talking about what it doesn't mean. And I want to just put up maybe you've seen this before today or something, but this is a typical problem with explanations of deep neural networks. A lot of people try to explain neural networks, but it doesn't really work very well. And that's because neural networks are not actually designed to be interpretable. So there's no reason why they naturally should be. And so this kind of explanation, this one kind is particularly bad. It's called an attention map or a saliency map. And it's supposed to give you the explanation for why this is classified as a husky. Okay, and indeed it highlights the right part of the image. Okay, so you think you understand the network, you think you might even trust it, but then you look at what else it's doing. And here I'm asking it for why the image has a musical instrument in it. And it gives me almost the exact same explanation. Okay, so it's just a, it's just not a good explanation method. It's telling you what pixels it's looking at, but it doesn't tell you what it's actually doing with those pixels. So our first approach to dealing with that is to use case-based reasoning. So case-based reasoning is kind of like K-nearest neighbors. It's like, this case seems similar to this other case I've seen before. It's kind of like what Dr. House does. I don't know if you guys watch that TV show, but I love that TV show. And you have a doctor on the TV show and he looks at the patient and he says, that patient has a green foot. I've seen a patient with a green foot. He had chilblains. So maybe that's what it is, But also the patient has a weird heart condition. So he reminds me of this other patient who had a similar heart condition. So we wanted to get the neural network to try to reason like this. So we want to have the network reason about an image based on its similarity to other prototypical cases. So here is our prototypical network explaining to me why it thinks this bird is a clay-colored sparrow. And I like working on the bird watching data set because I don't know anything about birds. So anyway, it's going to pick out different parts of the bird and tell me why it thinks this looks like a clay-colored sparrow. So it says, so the network's saying, I think this part of the bird looks like this part of that bird. And this is a prototypical clay-colored sparrow. And I think this part of this bird looks like this part of that bird. And this is a prototypical clay-colored sparrow. And then this part looks like this, and this looks like this, and so on. And this is how the network actually reasons. And the prototypes here are learned. They are not selected by experts, they are learned. And the ways to compare images, that's actually learned as well. Now, because the neural network says this looks like that, and this looks like that, and this looks like that, we called the paper, this looks like that. And the main idea of the paper is that it adds, you take your favorite black box, and then you add an extra layer to the network just before the very last layer. And the layer does this comparison based on case-based reasoning and prototypes. And again, the prototypes are learned during training. So let me repeat that again. So you take your favorite black box. So here's your favorite convolutional neural network for computer vision. And then you create, you make it interpretable by adding this extra prototype layer just before the last fully connected layer at the end of the network. And we usually select 20 prototypes per class. and the number of prototypes that can be chosen as a parameter. And then the network in this layer, it scans the image looking for parts of the image that look like each of the prototypes. Okay, and so that's how it's working. All right, so let me give you a little more detail on what it produces. So the network is now going to explain to us why it thinks this bird is classified as a red-bellied woodpecker. So it takes the bird and it says, well, I think this looks like that part of this bird. And in fact, I think it's very similar. I'm going to give it a similarity score of 6.499. Okay, so I give it this is a very high score, by the way. So I think this is very similar to that. And then there's a class connection weight, which tells you how important this bird is to this class. So how much this image looks like a red-bellied woodpecker. Okay, so this is how similar my test case is to the prototype, and this is how important the prototype is. And then we add up the points for all 20 prototypes and get a score for the red-bellied woodpecker class. And we do that for all of the different classes. So here I'm showing you the same calculation for the next highest rated class, which is the red cockaded woodpecker class. But interestingly, red cockaded woodpeckers do not have red heads. And so it can't gather any points from the comparison of the bird's head. And so it just has to use the feathers. And it just can't get that many points based on only the feathers. And so it says, okay, no, I think this is why it's a red-bellied woodpecker. I get the most points for that class. Now, I'll show you an example where it messes up. So here, in this case, we started with a base model of DenseNet 161. We added the prototype layer, and it got this bird wrong. Okay, so this is a warbler, and it got confused as to whether this was a prothonotary warbler instead of a Wilson's warbler. It's actually a Wilson's warbler. Sorry, got it wrong. Okay, so it gives you some evidence for why it's a Wilson's warbler. It's looking mostly at like the eyes and like some aspects of the feathers. But the fact is, it actually really looks like a prothonotary warbler. I mean, I don't know if you can see this, but I'm looking at this bird's, face, and I'm looking at that bird, and they look very similar to each other. And so that explains why I got confused. So, all right, fine. Now, as I mentioned to you, I can choose any base model I want. So if I swap out the base model with a VGG16 model, then it turns out VGG16 actually gets this one correct. And if we look at what happened, you can see that there's certain information that it's not using. And in particular, the top of the bird's head. So as it turns out, Wilson's warblers generally have a black spot right on top of their head, but this bird doesn't. And so I think what's going on is that this might be a baby Wilson's warbler. And so as it turns out, baby Wilson's warblers kind of look like prothonotary warblers. And so maybe the network, maybe that's the reason that the network got confused. All right, so we've been looking at, comparing the accuracy of the prototype network to its base networks, to the black boxes that we started from. And what we found is that on this, and this is a benchmark data set in computer vision. This is one of the main benchmark data sets. This is where, high neural network performance was born, right, with this data set. And these are the accuracy levels that we get from the different base models. So a whole bunch of base models, we get accuracies between these numbers. And then when we put the prototype network in and retrain it, then we get numbers that are actually within this same range. And then if we take a whole bunch of these prototype networks and stack them, okay, so instead of a linear model at the end that's a combination of 20 prototypes, you get it, if you stack them together, it's more prototypes. It's still interpretable because you're still doing case-based reasoning. It's kind of a bigger network. But if we put them all together, we actually beat the accuracy of the black boxes. So what I'm saying is that even for the most difficult computer vision problems, even for the benchmark data sets, even for the places where the deepest of the deep neural networks were born, We can still have an interpretable model that has the same accuracy as a black box. So I'm going to switch over to a different notion of interpretability next. Okay, so I'm switching topics here. So instead of using case-based reasoning, I'm going to talk about a different type of interpretability for deep neural networks. So again, I'll start with explainability techniques, which seem to not do so well for this particular type of explanations. And that is to try to figure out what concept each node is detecting. There's a lot of people doing post hoc analysis on deep neural networks to try to understand what the nodes are doing. So there have been cases where people claimed that a certain node was like a grandmother node or like a lamp node. Like, you know, the information about lamps, it's traveling through that node. That node is the lamp node. But I think a lot of the work in this area is kind of bogus. So people say, fine, what we're going to do is figure out if all the lamp information doesn't go through one node, well, maybe it goes through, you know, multiple nodes. Like if you look at where all the lamp information is activating, it's some combination of node 1 and node 2. It's activating node 1 more than node 2. Okay. And so people have been trying to do all kinds of summary statistics on these what they call concept vectors. Now, I claim that if you actually want to know what a node is doing, you probably should give it some instructions instead of assuming it's going to do what you think it's going to do. So that gets to the second approach on interpretable deep neural networks, which is to try to disentangle the neural network's latent space so that all the information about a concept flows through just one node. So this is what we call concept whitening. And I'm going to tell you about how this approach works. So as I mentioned, CNNs are not naturally disentangled. So let's say that what we really want is sort of all the information about airplane that the network needs for whatever it's predicting to go through just one node, and all the information about car just through one node, and so on. Okay, this is not what a typical neural network does, but we're going to create one that does this. Okay, so let's go back though. Before I do that, I'll talk about the idea of what a concept vector is and kind of why it doesn't work. All right, so let's say that we take a standard CNN, and I want to consider the latent space of the batch neuron layer. So what I'm doing is plotting the activation of each image, and I'm showing you kind of which neurons are activated and how much they're activated. And so this is kind of the idea behind concept vectors. Like you have, maybe these are lamps, and so lamps light up neurons 1 and 2. These are trucks, which light up neurons 1 and 2 as well. And then, you know, this is some other thing. Now, what people often do, like I said, is they create these concept vectors that point toward the different concepts. But the problem with that is that these concept vectors don't really make that much sense because the lamp information might not be centralized in one direction. It might be all over the network as well. Also, you might have concept vectors that are kind of close together. Like these are both pointing in the same direction, even though they're two completely different concepts located in different parts of the space. So you kind of want to be careful about interpreting these concept vectors. Now, what we wanted to do instead was to try to disentangle the space by replacing the batch neuron layer with something that would disentangle the space. And in particular, we want it to whiten the space, so decorrelate and normalize it. So whiten it, and then afterward align the axes with the concepts that we're actually interested in. So now neuron 1 actually is representing all the information about airplanes that we actually are using to predict the outcome. And then neuron 2 is handling all of the car information. And neuron 3 over here this is off in some other direction, handling whatever other information. All right, so the concept whitening technique, it does really kind of funky things when you add it to different layers. Now, if you add it to a very early layer, then the network really isn't capable of producing the whole concept. So it just produces the information that it can about it. It creates kind of an abstract preliminary version of a concept, like kind of a rudimentary version of the concept. So for instance, if we're trying to predict airfields and we have a neuron in the second layer dedicated to, airplanes, then it creates its own notion of what an airplane is in the second layer, which happens to be a gray object on a blue background. And again, we didn't tell it to do this. We told it, just route all the airplane information through this one node. And this is what it came up with by itself. And it's interesting because none of these are airplanes. They're all like sea creatures. But that's what the network is doing at the second layer. That's its most extreme version of airplane in the second layer. And then for bed, it created an abstract notion of bed, which is sort of warm colors, it looks like. And then for person, it seems to create some kind of interesting textures. And then, so in earlier layers, color and texture information related to the concepts tend to be represented along the axes, because you don't really need to have a whole airplane to detect airfield. You just need sort of the part of the airplane that is like what it can represent in the second layer. On the 16th layer, the concepts are much more well defined, because it actually has the capacity to represent airplane, and it's actually using airplane information to detect airfield and bed information to detect bed. Okay, so it can be really interesting if you want to trace what happens over the layers for a particular image. And this one is really interesting. This is an image of an orange sunset. So as you know, this has neither a bed nor an airplane in it. So what's going to happen? So early on, the network says, well, it has kind of warm colors. I think it's a bed. I think it's got a bed in it. Doesn't have an airplane. No airplane, because it's not a blue object with a gray thing in the middle. So, okay. Great, so that's what it does early on. And then as the layers, as we move through the layers, it starts to think that maybe there might be an airplane in the image, and maybe not so much a bed, because it's seeing the blue sky and the clouds and so on, and saying, maybe I think it's more of an airplane. And then as time moves on, it starts to realize, wait, hold on a second. Maybe there's no airplane in that image. Maybe it's less of an airplane than I think it is. Nope, maybe it's more of an airplane. So it's like a race here. It's like, maybe there's the bed, that's the airplane, it's the bed. But in any case, at the end of the day, it decided that it really does not have a bed in there. Maybe an airplane, but definitely not a bed. Anyway, so you really can get a sense of kind of the way information is flowing through the network and what the network is using, what information the network's actually using to make its predictions. Now, what we've noticed about CW is that we don't notice any sacrifice in accuracy over the black box that we started from with the batch norm layer. And the accuracy with CW is on par with standard CNNs. It's also very easy to use, because if you have your already trained black box and you replace the batch norm layer with the CW module, then all you need to do is one additional epoch of further training. So one pass through the whole data set. However, you do need to have training data to define the concepts for defining the axes, but you would need that anyway if you were going to do concept vectors. So that's not something that's unusual. And then again, a great benefit is that for free, you don't need to create concept vectors, because the concept vectors are actually the axes of the latent space. All right, so just to summarize what I've talked about in my talk, an interpretable model is constrained. It's a constrained model that helps you understand it better. And I've given many different definitions of these constraints, starting from sparse being sparse and having integer coefficients. Those are constraints, as well as forcing a neural network to do case-based reasoning in this looks like that paper, as well as disentangling the latent space of the network in the CW paper. So these are all different types of constraints that we've added. Now, as I mentioned, evidence does not support an accuracy interpretability trade-off. And I've given you examples in deep learning specifically to aim at this particular statement, where it's really unclear to me that you would truly ever need an honest to goodness black box, because even in these cases where we have the most accurate, the deep neural networks that are the most accurate for benchmark data sets, even in those cases, we can add interpretability constraints without losing accuracy. And obviously there's the nuance that I mentioned, whereas with tabular data, most methods perform similarly. So it opens the box up to being able to create very sparse models that are just as accurate. So the example I gave was scoring systems. And then with neural networks and computer vision problems and time series problems and other things, you have to define interpretability differently, but you can still get to where you want to go without losing accuracy. And I gave you, again, these two examples of where that happens. And so these are my versions of the extremes. So from very, very sparse models with integer coefficients that are linear, all the way in the other end to these deep learning models for computer vision. All right, thank you.
Thank you so much, Professor Cynthia, for your excellent talk. And I think that we are now open for questions, comments. Does anyone want to start? Should I do the kickoff? Maybe I'll start myself. Professor Cindy, you questioned basically the trade-off between interpretability and accuracy. In the papers, we often see those statements about the tension between those two aspects. And you seem to support that interpretability is like a good prior to in learning, because it really benefits probably, or at least doesn't penalize accuracy. But is it penalizing any other aspect? For instance, in deep learning with neural networks, they are often said to have these distributed concepts in the network. And are we losing some robustness of the models against, I don't know, noise, loss of part of the model, let's say? Are we losing anything? Is the trade-off not between accuracy and interpretability, but between interpretability and something else?
Yeah, I think there's definitely a trade-off, but I think the trade-off isn't robust. I think robustness and interpretability actually work together. I think the trade-off is computation. Whenever you try to add in those additional constraints and still optimize accuracy subject to those constraints, you now have a more difficult constrained optimization problem. And it just tends to be much harder to optimize, especially things like sparse linear models with integer coefficients. So as I mentioned, we have a mixed integer nonlinear program there. It's so much easier just to run logistic regression and not worry about the sparsity, right? As well, for something like this looks like that network, it's called Proto-PNet. It's just much harder to optimize than a regular deep neural network, which obviously has been tuned by, hundreds and maybe even millions of graduate students. I don't know, thousands of graduate students. Whereas the this looks like that network has not been trained by that many students, maybe like 3 students. So I do think there is a trade-off, but I think it's computational. The interpretability trade-off is not the same as the fairness trade-off. I think with fairness, you lose accuracy, but you have to. There are inherent trade-offs in fairness, but I don't think, I haven't seen any evidence that that's present for interpretability. And that's why I gave you so many examples, was to kind of really show that I haven't found this trade-off.
But that computational trade-off is on the training, but on inference that doesn't hold, right?
On what?
Because on the inference, on the testing, on using the model, well, it's more difficult to train, let's say. It takes more time, more effort, but for the use of the model, that is not an issue. It's not a problem.
It actually benefits test accuracy, because if you actually understand the model and why it works, then it tends to actually be better, especially with medical data sets. Like we're working on applying this looks like that model to mammography. And those data sets there's so much confounding in the data set that if you don't tell it what to do, it's going to use all kinds of weird information that you don't want it to use. And so if you actually ensure that the model's looking at the right aspects and doing the right kind of comparison, it actually generalizes better than if you didn't do that.
Does anyone want to raise a question? Yes?
Yeah, I have also a question if I'm allowed to. Yeah, thanks a lot for this inspiring talk. It was very interesting. I also liked very much your bird classification scheme and methods. And the question is, for the bird classification, you somehow assume that the information is also locally spread around the image. So you say this part looks like that part in the other image, and this is true for the nap or the head or the belly and so on. So what happens if you have some data where all this information is more mixed? For instance, if you have medical data and you have a lot of different properties of the image that are all at the same physical location in the image, but have different aspects. And is it possible to extend such a scheme also to visualize examples from other data sets where this information is not clearly separated spatially?
Yeah, so like I said, we actually are applying it to mammography, where where mammography is a mess. I had no idea what a messy field this was until we entered it. I mean, I can't even read mammograms, and I've been working in this forever, and I can't even understand what's in them. So even my human visual system is just terrible for this. But if we let the network do whatever it wants, it uses things like the density of the breast tissue, which it's not supposed to use, right? You're not supposed to use the density of the breast tissue to determine whether a lesion has certain properties of it. And so this looks like that network, what it used to do was use all kinds of weird crap. You know, you could see what it was doing, and it was doing the wrong thing. And so we had to convince it to do the right thing by adding additional data. We actually had a bunch of radiologists go and label all the images to try to get it to sort of reason the way a human would and look at the right part of the image. Yeah, does that answer your question?
Yes, to some extent, but how does it look like then, the visualization? So if the network goes wrong, and so what does it actually show then?
It'll highlight parts of the image that are totally irrelevant.
Okay.
And show that it compares it to this other part of this other image.
So it's clearly evident that this is a mistake, and then you can retrain. Yeah. Okay, thanks.
Yeah, you can see, like, and sometimes with the birds too, sometimes it uses the background. Like if the bird is a water bird, it'll use the information about, like, oh, I see some water in the background to classify this bird. It's like, no, you're not allowed to use that. And so we have to actually manually throw that prototype out because it's not allowed to use the confounding information.
Okay, thanks a lot.
Let me also ask a question related with a bit of this and the ensemble. And you said that the ensemble of interpretable models is still interpretable, at least for this model that you use for birds. It's not totally clear to me that a large ensemble is still interpretable. Could we have like contradictory explanations in your models? Could one try to say that decision is this one and because of this and this, and another one explaining in an opposite way that goes against the other explanation?
So okay, that's a good question, and I completely completely appreciate your point about this is not sparse anymore. It's not like it's not 20 features. It's now like 80 features because you combined a whole bunch of networks, and I totally agree with you. And I would love it to be sparser. And to be honest, there are people who've extended the proto-PNet to actually be nonlinear in the last layer. They've actually created decision trees in the last layer that actually I think work a little bit better than our linear models and actually create sparser, more accurate models. So I'm not saying that we've done the best thing since sliced bread. I think this other team, who I don't even know, it did quite a good job on that. But So it is possible that the network would be using incorrect information, like I said. And so you were asking, is it possible that you have one subnetwork doing this thing and another subnetwork contradicting it or using information going the opposite direction? It is possible because the networks get things wrong. But luckily, you can see that, okay, this comparison here, this does not look like that. And so I disagree with the network on this point. And now I can disregard this piece of information and try to help retrain the network and fix whatever problem that is, so that the next time it hopefully won't make that same mistake.
Thank you. Anyone else that would like to intervene?
Can I make a question?
Yes, sure, Alphonse.
More than a question, is just a little experiment. Given that people around me, because I was discussing with my mates in my department this same question. How many of us remember the classical classification of machine learning systems from Michi? I don't know if from the 80s or something like this, about weak systems, weak machine learning system, a strong and ultra strong machine learning system, because it seems that we are worried about the definition of explainability when, at least from this year, there is something hint about that. So my question is, how many of us are more or less concerned with this old classification on machine learning?
I think you should write a paper on this, explaining these old categories and how they relate. So I'm not familiar with these old categories. That's a little bit before my time, but I know that there's a lot of work that's been forgotten. So for instance, let's see if I can, I'm just going to share my screen again here. So this paper, I don't know how many, maybe you might have seen this paper, but it's called Stop Explaining Machine Learning, Black Box Machine Learning Models for High Stakes Decisions and Use Interpretable Models instead. And this paper kind of goes through, there's some very old papers on interpretability that people have completely forgotten about. Like there was a paper from 1980 by Robert Holt that was called, simple models can predict surprisingly well, right? So he knew back in 1980 that very simple models were quite good. And then also there was a paper, there was some writing on the internet called the Comprehensibility Manifesto, which basically said, I don't really know how to define interpretability. And this paper was from, I didn't even know what, it was from a really, really, really long time ago. And I feel like a lot of the works on explainability in particular, I don't use that word myself. I use interpretability for models that are inherently interpretable to kind of contrast with explaining black boxes versus using inherently interpretable models. But a lot of the explainability work, it's like the field started in 2016, which is ridiculous because, I mean, I've been working on this for at least 10 years. So I mean the literature and I've been citing work from 1980. So I feel like a lot of the old work is kind of has been sort of forgotten about or shafted, and I think that's I think it's really a pity and a shame that we're sort of thinking that, oh yeah, everything started in 2016, because it's not. And I don't even think the work from 2016 is very good, because it's about, should I trust you? But that work wasn't about should I trust you, it was about approximations. It wasn't even about explanations, it was about approximation. And you shouldn't really trust an approximation to tell you actually in the model. So yeah, I think forgetting about old literature is really problematic. So I hope you write something and send it to me.
No, it's just for try to build bridges between. There are lots of abuse of language, because we tend to say formal methods in opposition to statistic methods, when both of them are formal methods, in fact, or machine learning more to statistic approaches than declarative ones. So I think that it could be a good idea. We are planning to do that. Try to to build bridges between the so-called formal and numerical approaches to machine learning, because it seems that interpretations, explanations, anything that is related with that is declarative in its nature. So it could be interesting to try to take advantage of people that seems to be working in another world, because it's tough to find people from formal methods interested in work with people from numerical methods and the opposite. So yeah, I think that it could be good for everybody to build bridges in this direction, and this was our main goal to push in this line, because we feel that this some gap that should be filled as soon as possible.
Awesome.
That's all. It was a small experiment that I thank you to have answered my question.
Thank you. Thank you. I know that we are a bit over our time. I don't know if there is one last question. I don't think so. So I think that we can now then stop, and thank again Professor Cynthia for the talk and for the participation in this workshop. It was great to have you with us, and I hope that we can in the future collaborate again in this kind of events. Yes, thank you.
Thank you.
Felipe, do you want now to take the lead?
I'm having some connection problems, so I think we can move along to the second oral session, and our chair, that is Wilson, can take it from here, please.
Yep.
Thank you so much.
So,
thank you.
Hello everybody, and thank you again, Professor Cynthia. The talk was really interesting, and Tiago and I will host this final oral session. And the first paper to be presented is entitled Focused Lrp, Explainable AI for Face Morphing Attack Detection. And I think it's presented by Clemens Zeibold, and it was a joint work with Anna Ilsman and Professor Peter Eisert.
Hello everyone, and welcome to my talk, Focused Lrp, Explainable AI for Face Morphing Attack Detection. I'm Clemens Zeibold from the Fraunhofer Institute in Germany, and I represent a new method to analyze the decision-making process and feature activations of deep neural networks for the detection of morphing attacks. Let's start with a short introduction to face morphing attacks. A face morphing attack is a harmful use of a synthetic image that contains characteristics of two different subjects. For example, such an image could be used in an ID card or passport, and in this way, two subjects can share their identity and one can travel or do business under different identity. Today, there's a large variety of freely available tools to generate such an image, which is called morphed face image or simply morph. The images that are generated in this way are proven to be able to fool even commercial facial recognition software, such that both subjects match against the morphed face image. Here you can see an example of a morphed face image. It's the image in the center, and the morph resembles the two different subjects that are shown in the image on the left and on the right. Our objective was to develop a framework that can highlight traces of forgery in morphed face images. The output of a DNN for classification is usually only a decision for a class, or rather a score for each class, but per se it does not provide an explanation about its decision. Inspired by the DNN interpretability method Lrp, we developed Focused Lrp, compared it to Lrp, and identified the strengths of our proposed method. The structure of my talk is as follows. First, I give a short overview on how a morphed face image can be automatically generated. After that, I present the DNN-based detector that is analyzed in our work. Subsequently, I explain Lrp, a tool that explains which regions of an image are important for the decision of a DNN And after that, our new extension Focus LRP is explained. Afterwards, a framework to evaluate and judge the relevance assignment by LRP and FLRP is explained. Finally, I conclude my talk with our experiments and the identified strengths of FLRP. Here you can see a pipeline to generate morphed face images that is usually used to generate them, also by freely available tools. To start it, we need one image from each of the subjects that the morph should resemble. In the first step, we calculate for each of these images the facial landmarks and transform the images so that they are aligned. In the next step, we blend the aligned source image using additive alpha blending. The result of this process contains visible ghosting artifacts around the silhouette of the head and the hair. To get rid of these artifacts, we insert the inner part of the face of the blended image into one of the aligned source input images using Poisson image editing, and thus we obtain the final morphed face image. Our detection method is based on a deep neural network and a pre-processing step to obtain a normalized input for the network. The input image is rotated and cropped so that the eyes are on the same height and only the inner part of the face is processed. Finally, the image is rescaled to a fixed size. This processed image is then fed into a DNN. In our experiments, we use the VGGA architecture, which consists of several convolutional layers that can be viewed as feature extractor, followed by fully connected layers for the classification. In our experiments, we trained the network as naive two-class problem, and the output classes are morph and genuine image. We had about 2,000 genuine images and generated the same amount of morphs. These images are split into a training set of 70% of all images, a testing set of 20%, and a validation set with 10%. And here just some details about the performance of the detector. The attack presentation classification error rate is 4.9%, the bona fide presentation classification error rate 2.6%, and the equal error rate 3.3%. Common interpretability methods for DNNs assign to each pixel in the input image a relevance score that describes the contribution of this pixel to the decision of the DNN. The relevance assignment can be visualized using heat maps. In this example and in the following, we use the Parula color map to visualize the relevance assignments for an image. Blue indicates no relevance at all, yellow a high relevance score, and green something in between. So in this example here, the specular highlight on the nose and the right eye are most important for the decision of the DNN. A method to obtain the relevance for each pixel is LRP. LRP propagates relevance that is assigned to one neuron in the last fully connected layer that describes the class back to the image. The relevance is propagated layer-wise from the last layer to the input image using a set of rules. These rules are designed so that LRP shows which regions in an image lead to an activation of the class by assigning to these regions large relevance values. Thus, LRP answers the question, which regions in an image lead to an activation of the class. But in terms of morphing detection, this is not always equivalent to which regions do contain morphing artifacts, even if we start LRP from the neuron for the class Morphing Attack. Inspired by LRP, we propose FLRP, a tool that answers this question, which regions do contain morphing artifacts. In contrast to LRP, it does not assign a start relevance to a neuron in the last layer, but to a set of neurons in the last layer of the feature extractor. These relevance values are then propagated to the input image with the same set of rules as used for LRP. By this concept and by choosing neurons that are artifact aware and thus have a high activation if the image is a morphed face image, our method focuses more on the question, where are artifacts that are detected or detectable by the DNN? For the selection of the start neurons, we are looking for neurons that are discriminative and have a large activation if the image is forged. To this end, we calculated the output of the feature extractor for all images in the training set. Then we calculated an activation threshold for each neuron such that below this threshold is the same amount of genuine images as morphed face images are above this threshold. Then we selected for each channel the neuron that best separates forgeries and genuine images. This results in 49 different neurons that we use to start FLRP. In order to evaluate the different relevance assignment methods, we extended a common approach based on substitution of relevant regions. First, the relevance is calculated for the input image of interest, and then based on the relevance, a fixed number of pixels with the largest relevance is substituted. Usually, these regions are substituted by a default value or values from a predefined distribution. In our scenario, and since the DNNs are always fed with aligned images of faces, this would create data far away from the data distribution that was used to train the network. So we developed a more sophisticated method. We use one of the aligned input image to get the color values for our substitution. Actually, we substitute the selected most relevant regions by the corresponding regions of the input image. The final image without the as relevant highlighted artifacts is then fed into the network, and the change in the decision making is analyzed to analyze the quality of the relevance assignment. We use this proposed approach on our morphed face images with different amounts of substituted pixel and analyze the differences in the loss function of the DNN and the error rate in terms of APCER. For these metrics, we expect that the better relevance assignment method leads to a larger error. The differences between FLRP and LRP are small, but FLRP performs better even though it does not consider the classifier. In order to get a better understanding of the differences between the relevance assignment of LRP and FLRP, we analyzed the relevance maps more in detail and studied how similar the maps for LRP and FLRP are and where exactly the differences are. To this end, we calculated the transparency maps for a fixed amount of pixels and calculated for each image the normalized difference between the transparency map calculated by LRP and by FLRP. The results are shown in this histogram. A value of 0 means that the transparency maps are identical, and a value of 1 that they do not overlap. Even though they mostly overlap, there's a large peak at the other end. We analyzed these images and saw that the output for FLRP and LRP strongly differs for most morphs that are not detected, or the DNN's decision has a low degree of certainty. In these cases, LRP often assigns most of the relevance to the part of the forgery that does not contain easily visible artifacts. But FLRP, on the contrary, does still assign relevance to these forged regions and thus highlights traces of forgery that are detected by the DNN. In this example, the image was falsely classified as genuine image, but it's a morph. It contains easily visible artifacts at the nose and the right eye. At the right eye, you can see that the specular highlights are somehow strange, and at the nose that there are some ghosting artifacts around the nostrils. However, LRP assigns most of the relevance to the genuine-looking left eye and no or only marginal relevance to the visible artifacts around the nostrils or the right eye. FLRP was still able to detect and highlight the traces of forgery. Here you can see another example where LRP and FLRP strongly differs. LRP assigns most of the relevance to the right eye, that is quite valid, while the obviously morphed left eye only gets relevant assigned by FLRP. In this example, the DNN had a low degree of certainty in its decision. However, in most cases, LRP and FLRP show quite similar results as shown in this example. It shows a morphed face image and that was detected by DNN with a very high degree of certainty. Here, both methods assign relevance to both eyes and to the nose, and the difference is mostly in the strength of the relevance. So with FLRP, we proposed a new method that can highlight traces of forgery, even if the decision of the DNN is wrong or with a low degree of certainty. In these cases, Lrp assigns relevance often only to genuine-looking regions instead of assigning it to easily visible artifacts. In other cases, Lrp and FLRP perform quite similar, that there's no disadvantage in using FLRP instead of Lrp for detection of morphed face images. In future work, we plan to study the effects of image improvement and image compression on Lrp and FLRP. We also want to test our evaluation framework, Lrp and FLRP, on DNN-based morph detectors that have been pre-trained with a complex multiclass pre-training. This complex multiclass pre-training usually leads to a very complex structure in the classifier and is difficult to interpret by Lrp. We also want to extend our framework so that it can work without a reference image. I thank you for your attention and hope you enjoyed my talk.
Okay, thank you very much, Clemens. Very interesting presentation. And so we have here Clemens. So if there are any questions, feel free to ask Clemens. Are there any questions?
If there are none from the audience, I can make, because I have some.
Go ahead.
Once again, thank you very much for your presentation. I was wondering also on the talk by Peter Heisert, but I guess that the work is quite related, so I guess I can ask this to you. In 2022, if let's say if we have an image of a person, of a real person, okay, so it's bona fide, but that image has some kind of, let's say, deficiency, so a scar, damaged eye. How do you think that this could trick our current state-of-the-art models, or is it possible to make our models also robust against those type of deficiencies, let's say, because the distribution of data, it should be different, right? So the model perhaps would classify it as a PA, a presentation attack.
We can't really be sure that it's classified as an attack because it's not in the data distribution. The network just doesn't know what it should do with, for example, a scar. And I think especially for these cases, interpretability in terms of which regions lead to indecision are very, very important, because if the DNN decides that, for example, the image is a forgery because some kind of strange structure in the eye, it might also be caused by contact lenses. And if we can provide this additional information to a human inspector, he can check whether it's something that is really in the space or really some kind of medical anomaly or medical issue, and use this information to make an own decision.
Thank you.
But in general, it's difficult to say what will happen if we test on data that are not in the distribution of the training data.
Yeah, that would be a follow-up question. So what would happen if we, let's say, present some kind of unseen setting of an attack, and what would be the behavior of the model?
So if we present what exactly?
Yeah, if we let's say that we learn a new, let's say, a new PA. So we were able to learn a new type of a presentation attack, and then we present this attack to a framework like the one you are presenting. What would be your intuition on that?
It's difficult to say. So what we also did in another paper was we tried to add more variety in the training data for the forgeries. And by adding more variety in the forgeries, we saw that the network is also able to abstract better to other kind of attacks. But of course, if we go too far away or can create the perfect attack, it might stay undetected. And but by trying to add more examples and a larger variety of examples, also of attacks, we saw that the network is able to better abstract also to new kind of attacks or new kind of image modifications.
Thank you. Thank you very much.
I just have a quick question. So if I understood correctly, with the focused LRP, So focused LRP and LRP, when the decisions are correct, they typically show the same regions. But when the regions are incorrect, like focused LRP is much better, right? Okay.
Yes, definitely. If it's incorrect, and also if the network is not really certain about its decision. Yes,
exactly. But and what I was thinking was like, okay, so that might be an indication that the problem is in the fully connected layers. And did you think about like retraining that part to see if the explanations produced by LRP changed and became similar? Because like if the focused LRP explanations are highlighting the right regions, it means that the feature extractor is doing the correct thing, and probably the problem is in the fully connected layers. So, yeah, it's just if you thought about that.
Yes, we also thought about substituting the fully connected layer by more simple models, and hopefully that's something I can publish in the future.
Okay, nice. Thank you. Thank you very much.
And we also saw that the feature extractor, or the neurons in the feature detector extractor, can already decide quite okay whether an image is a morphed face image or a genuine image. So we also think that using a very large fully connected layer might be a little bit of too much for such a simple two-class problem.
Mm-hmm. Thank you very much.
Of course, it's difficult to find a better substitution without losing accuracy.
Yeah, of course. Thanks. Okay, so
I have one question.
Okay, yeah, please be quick.
Thank you for the presentation. It's interesting, and I wonder if focused LRP work against the adversarial attack, like adversarial sample, because I saw the previous work about the LRP. There is one section about the analysis of adversarial attack. I wonder focused LRP still works against that attack.
We haven't tried it yet, but as far as I know, there are some publications that show that the adversarial attacks doesn't have such a strong influence of the generation of the heat maps. But we haven't tried it yet for the face morphing attacks, but it's a very good point.
Okay, so you mean the heat map, it doesn't look very clear for the adversarial attack, right? It's not like the morphing face attack.
So for the we also tried different kinds of adversarial attacks in another publication, and but they are something completely different. So for the face morphing attack, we don't need any kind of information about the detector, about the neural network. But of course, for the adversarial attack, we do at least have something that describes the process of the network, so how the decisions can be changed.
Okay, I see. Thank you. Thank you very much.
Okay, thank you very much, Clemens. And now we will go to our last presentation of this workshop with a paper entitled Unexplainable Attention-Guided Iris Presentation Attack Detector, which will be presented by Kunjian Shen and was done in collaboration with Aaron Gross.
I'm going to present our work on designing. Hello, everyone. Today, I'm going to present our work on designing explainable attention-guided iris presentation attack detector. This is joint work with Aaron Ross at Michigan State University. What is a presentation attack? A presentation attack entails presenting a biometric sensor with a fake or deliberate altered biometric trait in order to fool the system. Presentation attack can be launched using printed iris, contact lens, and artificial eyes. In order to circumvent or deflect such attacks, we need to come up with presentation attack detection solutions. The literature, most of the times, they use convolutional neural networks, and it can operate on either geometrically normalized iris image or unnormalized iris images. but all the aforementioned methods, they do not use the attention modules to enhance the paired performance. Generally, attention mechanism can be roughly classified into two different types. One is a channel attention module, another is the position attention modules. Here, we give a summary of existing attention mechanisms used in the literature. Some works have used the channel attention module alone, but most works they consider to combine the channel and the spatial attentions. For our proposed method, here is our given flowchart. We call our method as the attention guide iris presentation attack detector, which is short for AGPAD. So our proposed AGPAD includes both the generalization and the explanation capability. Here, we give the flowchart. Giving an iris image, it first imports to a backbone network. After that, we apply PAM and CAM to the convolutional feature maps. Then we fuse the outputs from those two different attention modules. In the end, we perform the flattening operation and input into the binary classifier. First, let's describe the concept about the position attention modules. For a given feature maps A, we will first input to the different convolutional operations in order to compute this position attention map. So this position attention map is used to measure the position dependence among the feature maps. After that, we need to multiply this position attention maps with the input feature maps in order to get the refined feature maps. And we also have to consider the short connection since we need to add back the input feature maps A. So here is the overall flowchart to compute the position attention modules. Given the input feature maps A, first it is imported to the convolutional blocks to obtain another feature maps B and the second feature map C. Then we can perform the reshaping operation to transfer the feature map over the B and the transpose operation as well. After that, we can simply multiply the transposed feature maps B with the feature map C to obtain the position map, which is also a two-dimensional image structure. After that, we can multiply the position attachment map with the input feature map D to get the refined feature map. Next, we are going to describe the channel attention module. So the channel attention module mainly, we still have to compute what we call the channel attention map Q. So the Q relies on the self-attention maps. So here the channel attention map Q is used to measure the channel dependency among the feature maps. And we also have to consider the short connection here, since that we have to add back the original input feature maps A. So here we give the overall flowchart for these computations. For the given feature map A, first, we still perform the reshaping operation and the transpose operations, and then we multiply back with the input feature map A. After that, we apply the softmax operation to get the channel attention map. And then this channel attention map will be multiplied with the input feature map A to get the refined feature maps. So after we obtain both the position attention map and the channel attention map, there are different ways to fuse them together. The first choice is that we can perform an algorithmized summation to fuse those two different modules. Next, second, we also consider to sequentially combine those two different attention modules. That means we first apply the channel attention modules, and then we apply the position attention modules. let's present some experimental results to show the advantage of our proposed methods. We evaluate the proposed method AGPad on two different datasets. The first dataset is called a JHU APL dataset. And this dataset is mainly used for testing purpose. So we have collected a large number of training datasets, and this training dataset is not overlapped with the testing datasets. And this testing dataset is further divided into two different sessions. The first dataset is called JHU1, and the second testing dataset is called JHU2. And they are collected in different sessions. And as you notice from this figure, the quality from the JHU1 is much worse compared to the quality in JHU2 dataset. Since we have seen a lot of occlusions and the blurring effect associated with JHU1. Another dataset we are going to test is a public benchmark dataset called Live Detect 2017. And we will follow exactly the same protocol as the computation. In order to perform a fair evaluations, we have utilized different metrics. The first one is the ROC curve, and we report the true detection rate at 0.2% false detection rate. So that's the metric that we used on the JHU APL datasets. For the experiment results on the Live Detect 2017 computation, we follow the same protocol such that we use the BPCER and the APCER. The first experiment result is that we run our proposed method AGPad on both the JHU1 and the JHU2 with different backbone networks. As you notice that the DenseNet backbone network gives the best performance. And here we also show the fusion results for all the three different backbones. Especially on the JHU2, the fusion results gives the best performance. So here is our table results. As you notice that with the DenseNet backbone network, we obtain 100% accuracy on JHU2, but we only have like 72% accuracy on JHU1. That means JHU1 is much more challenging compared to JHU2. As you notice that the paired performance could vary with the nature of different presentation attacks. Here we show the experiments on different presentation attack types. As you notice that the context presentation attack type is the most challenging one, and this is the context types that we need to pay much more attention. Next, we also want to show what's the impact of different fusion mechanisms for the attention modules. So previously we have discussed about the sequential fusion and the parallel fusions. And generally we have observed that the parallel fusion performs slightly better than the sequential fusion. And the hierarchical fusion, that means we extend from the parallel fusion, but trying to extract the features from different layers. And we notice that the hierarchical fusion performs much better in the challenging scenarios as observed in the JHU1 dataset. We also perform an aberration study to show the impact of the attention modules. Basically, we evaluated results on using the PM module alone and the CAM module alone. So we noticed that if we just use the PM and the CAM, we can get a much better performance compared to the baseline results. And of course, if we consider both the PM and the CAM together, that gives our best performance on both JHU1 and JHU2 datasets. So our work also wants to present some results on the explainable visualizations. In order to give the explainable visualization results, we use the graded CAM visualization schemes. So the graded CAM works by throw the gradients back from the class output into the convolutional layers in order to get the maximized outputs with respect to the class informations. GrandCAM can be used to highlight the important regions that correspond to a particular class predictions. Compared to other visualization schemes, such as series maps, feature visualization, or invert image representation, GrandCAM provides a much simpler way to visualize the importance of different input regions with respect to predicted class. Here, we show the GrandCAM visualization results before and after we apply the attention modules. The second row gives the results without using attention modules, and the third row gives the results after we apply the attention modules. Clearly, we can notice that after we apply the attention modules, the GrandCAM starts to focus more on the cylinder regions. We also present our visualization results on the pattern detections. So we apply the iris detect first, get the cropped iris, and then we input the cropped iris to the presentation attack detectors. Here we show the visualization results on the detections with respect to different PA types. In order to compare with existing methods, we also run our method on the public benchmark dataset, which is the Live Detect 2017 computation dataset. That dataset contains results for both known and unknown presentation attacks. As you know, for our proposed method, we compared against 3 benchmark algorithms, and overall, our proposed method gives the best performance. To conclude our work, first, we propose a novel attention-guided XAI framework for iris presentation attack detection that enables both generalization and explainability. We run the experiments on 2 different datasets and show the effectiveness on both known and unknown presentation attacks. Last, we show the visualization schemes in order to explain the performance of the proposed network. We also want to thank our sponsor of the IARPA for sponsoring this project. Thanks for your attendance. If you have any questions, please feel free to ask. Thank you.
So thank you very much, Kunjan, for your presentation. And you are here today to answer questions. So if there are any questions, please feel free to ask Kunjan. There was Indu. Do you have any question?
Yes, I do.
Okay, so feel free to ask them.
Okay, so firstly, very nice presentation by the author. I would like to ask that, since their contribution is the novel attention mechanism, so can you explain how is your method different than the state of the art, which is CBAM, and the other ones you have compared? So how is the spatial attention, position attention mechanism, and the channel attention mechanism different than what is already been proposed, and why intuition? What is the intuition behind, why it is performing better?
Yeah, sure. Thanks for the question. Actually, so in our paper, actually, we do not claim that the attention module is the novel contribution. So that has to be clarified because the attention modules has already been used in other research works. If you notice, like from the introduction. So
yes,
I would say that
is it like CBAM, the one which is like in CBAM? There
no,
also you have spatial and channel attention.
No, CBAM, it's a different attention module, right? If you look at the table results, I did compare like the PM and the CM with the CBN, and of course, like if you look at all the different attention modules, sometimes like you notice that some work they like it differs like slightly. You know, it always depends on how you like compute the weights for the channel, how you compute the weights for the spatial positions, right? So I would say that you know, sometimes like there will be like I would say a bit like a slight like difference like in the structures, like how do you perform the convolution operations like, in order to get those weights. So I would say that and of course, like if you look at CBM, like a convolution block attention module, or BM bottleneck attention module, they're also very similar to each other. So I would say
yes, they are very similar. Yes.
Yeah, the contribution of this work is more like you know, how do we actually effectively integrate those attention modules into our existing like iris presentation attacking works, and of course like if you look at the aberration study, like if you do not apply the position attention module or the channel attention module, the performance actually it's not good. But after you actually integrate those two different attention modules, and you can get like a really improve the performance. And the reason that we are trying to integrate those attention modules is that it also provides the way to understand, like, you know, once you automatically learn the weights, and you would need to understand that how those weights actually are connected to the certain portion of your input image, right? And especially if you try to visualize with the grand cam. So that's our purpose. Like basically, you know, once you integrate those attention modules, on one hand you can improve the pad performance. On the other hand, you can also provide some explanations about your pad performance. So
no, that makes sense. But my only comment is that, you know, it's not clear which method you have used. So the position attention mechanism and the channel one.
Actually, the architecture clearly explains, right? I presented the architecture about the position attention module and the channel attention module, right? So that actually clearly explains the method, right? And if you read the paper, I think you could get more details about the prior works, right?
Okay.
Yeah.
Thank you.
Okay.
Yeah, no problem.
Thank you very much. I don't know if there are any additional questions. We are a little bit late, but there is still time for a quick question. I don't know if any of you have anything to ask to Kunjan. Okay. If not, I will thank again Clemens and Kunjan.
Thank you.
And I will close this last oral session of this workshop. And I will pass the word to Philippa for the closing session. Thank you very much.
So just to wrap up very quickly, because we are 5 minutes late, and we know that you probably will go to other workshops in the afternoon. So we will wrap up. We just would like to thank to all the participants, and we are just going to announce the Best Paper Award and just finish. So if you allow me to just 1 minute to share my screen. And so it was really a pleasure to conduct this workshop. We hope in the future we will have other editions, and this was just first edition. It was very good to be embraced by the WACV conference. So there is a symbolic prize for what we consider best paper from the reviews that the papers received, and we would like to give the acknowledgement to the paper An Explainable Attention-Guided Iris Presentation Attack Detector. It was just presented now. And most of all, we would like to note that all the papers will be published under IEEE Explore Digital Library related to the proceedings of the WACV conference, and that also a special issue is being prepared in the Computer's Journal under the title Explainable Artificial Intelligence for Biometrics. This special issue will probably comprise not only the papers from the workshop, but it will also be open to other submissions. We hope this will capture interest from researchers that are working in this field. And we hope that this field will continue growing, which is the purpose of organizing this workshop. We would like to thank all the shares that belong to the committees and the supporters. Just a final word to the organization of the WACV conference and to all our authors and participants. It was a pleasure to have you here, and we hope we will have you in other future editions of our workshop. Thank you so much.
You're welcome. See you. Bye-bye.
Thank you. Have a good year.
Thank you, everyone. Bye.
Thank you, everyone. Thanks to the organizers.
Thank
Bye.
you.
Thanks.
Bye-bye.
Bye-bye.
Thanks, Professor Isaac.
Pronto, já
Podíamos
só
parar a
estamos nós.
gravação. Parar a gravação.
Ai, sim, sim.